One of the interesting things to do when you travel to different places is to explore cultural differences. And I want to explore a cultural difference right now. And this has to do with the culture of the classroom. Okay, so I know that you guys are all used to very large classes, and so you can't really ask questions, and you don't really ask questions, right? In an American classroom, I fail the students who don't ask questions. Okay, please, I need you all to ask a lot of questions. Asking questions is really important for two reasons. First off, is that if you don't ask me questions here, you're all going to ask me individually the same question, okay? Rule is, of course, that if you have a question, probably about 30% of the other people in the room have the same question. So I'll have to answer the same question a lot of times, and that will drive me crazy. And as economists, we believe in efficiency, right? And it's clearly Pareto optimal to answer the question only once, right? Okay, so you should ask. The other thing is that I don't really know very much about your backgrounds and what you know and what you don't know. And it's very easy for me to go too fast. I typically don't teach with these things because I like to use chalk so that I can't go too fast. But I can go through a slide pack in an hour if you let me. So I need you to slow me down. And also, as you ask questions, I will know what you know and what you don't know, and I can adjust my discussion accordingly, okay? All right, so normally, of course, when I travel someplace, I bend to the local culture, but now I'm asking you to bend to my culture and actually raise your hands, okay? So please do. All right, my name is Larry Blume. I have some connection to all these places, and my home is at Cornell University. My second home is in Vienna. I don't know what the Santa Fe Institute is about, and we are all here because of the HCEO. Thank you very much, HCEO. And I'm going to be lecturing on, you can see the title, Economic Models for Social Interactions. And so the first question is, first thing is I better pull this out, and I'm going to make the computer unhappy. Okay. And now I can use the mouse. Okay. Traditional microeconomics presumes that we have these individual agents who live in some kind of atomistic state, interacting with other agents only through some kind of market mechanism, communicating only through prices, so on and so forth. You're all familiar with the perfectly competitive model. Yes? Yes? Good. See those? Get it. Yes. Okay. Good. So there's no social structure of any kind, right, in these models, and we just look at pure market forces. However, we know that that in fact markets are only one part of the rather elaborate social lives that we lead, okay? And our behavior in markets is affected by our social lives in lots of different ways, right? So we tend to deal with people that we know. We learn from people that we know, right? A big issue in markets, something that we don't talk about in our basic microtheory classes, has to do with, for example, trust, right? So suppose that I go to a coffee stand and to buy a cup of coffee, and the guy gives me a cup of coffee, and I now have to pay him, right? How does he know I'm not going to just run off, right? Well, maybe he's a really big guy, and he'll come after me, and so I can't run off, right? But there's an element of trust in every transaction, and of course, at the grocery store or at the buying a cup of coffee, this is not such a big deal. But you can imagine that by the time we get to financial markets, this is a really big deal. Okay, and trust is something that exists kind of in some sense. It comes about by interaction with people. It comes about because markets are in some sense non-anonymous. Much has been written about the origins of of trust and how trust can support market activity. This is rather recent research. The importance of trust for economic growth. And people write about a transition from a kind of particularized trust, where I trust the people in my neighborhood, right, or the people in my region, but I don't trust a lot of other people, and how we move to a kind of generalized trust, which allows me to trade with people who are very far away, with whom I have no connection, and how this fosters economic growth, right? This is kind of an important growth story that some of you might have heard about. These stories having to do with the role of trust, the role of institutions in making markets work and fostering trust, right? This all has to do with this larger picture of social life and the way that markets are embedded in social life, and how, of course, social life, we don't study this so much, but how social life in turn is changed by markets. And this is what I'm going to talk about tools that allow us to investigate that. Now, we are particularly interested in income inequality, right? And we might imagine how our social lives affect the opportunities that we have for resources. I am sure, for example, that if one comes from in China, if one comes from a well-to-do area, right, living in a well-to-do neighborhood, going to good schools, there's a certain expectation that you are going to go to the university. You're going to try and go to the university. You study very hard for exams, et cetera, et cetera, et cetera. I'm willing to bet that there are other parts of China where, if you were born there and had lived there, thinking about going to the university would just not be something that's even in your mind, right? Am I correct in this assumption? Right, and this is, of course, a social phenomenon, right? We learn about our opportunities in life from our families, from our friends, from the communities in which we live and work, right? And the choices that we make rather early on in university with respect to education, with respect to the kind of training we get, have long-run consequences, right, for the life path of our earnings, and therefore where we're going to end up in the earnings distribution. Stephen Durloff, who could not be here this week, although he had intended to be, has written a lot on that. You should Google him, or you can ask me what papers are worth looking at here. He has a paper called The Membership's Theory of Inequality. You should write that one down. This is a paper where he talks about how your life circumstances are determined by who you know. There's a very important paper by Glenn Loury, Loury, on the same topic, having to do with, I think it actually has to do with social structure and the lack of capital markets. We might be talking about that later today if there's time. I have a very large slide pack, you can see, of 152 slides. I have never made it even halfway through these slides. And I don't intend to sacrifice your bodies and minds on the altar of completing these slides, a slide pack. But somewhere in there, there'll be some discussion of Glenn's paper if we get to it. Now, how do social life and economics interact? So here are really 2 points of view, okay? Karl Polanyi was probably best thought of as a sociologist, and he spent much of his career talking about how man's economic life is basically submerged in and determined by social relations. So, I've mentioned, for example, already, information, learning from people about opportunities that are available to us. But there's many more ways in which this works. Think about the competition for status, right? And think about what people do for status, right? Buying bigger cars and particular things that demonstrate, right, that your status, where you are in the social structure. And this is what Polanyi is talking about here, that basically our purchases of material goods, a large role, you would think from reading this that Polanyi doesn't think that people eat. He does think that people eat, okay? But he says that what you eat has to do in part with your signaling and maintaining a certain social status, okay? On the other hand, we have an economist, Jim Dusenberry, He says that in drawing the distinction between economics and sociology, he says that economics is all about how people make choices. Sociology is all about why they don't have any choices to make. There was at the time he said this, a kind of a school of thought that basically says that we are all the victim of social forces, and into social forces that basically determine the choices that we make. Whereas, of course, you know that in economics, we are all about free choice, right? Especially if we're at a University of Chicago connected program, right? Pardon me. So, however, so this is a distinction that economics and sociology are the two social disciplines that are most interested in the analysis of large social systems. But we think about these things in very, very different ways. On the other hand, I think in the last 20 years, there has been a great deal of convergence between economists and sociologists, between economics and sociology, in that, for example, many of us are now writing papers on the same topics, using some of the same statistical skills, same techniques, and asking similar kinds of questions, and in particular in areas having to do with income and stuff like, and wealth dynamics and things like that. There's also a kind of a convergence of questions. Both economists and sociologists have been very interested in talking about how social life affects economic decision making, and we're going to actually survey some of that work today. So I think there now is a community. That's not to say many economists, of course, still say sociology, right? And many sociologists think that economics is what you get when you learn math rather than useful stuff. It's not to say that these fields have merged. They're very far from merging, right? But there are now many, many points of contact. And I can't say what it's done for sociology, but I can certainly say that it has enriched economics a great deal. What do I mean by social interactions? I mean, for example, the way in which, and today we are largely going to talk about the way in which peers influence our social behavior. Right? By peers, I mean my friends, my relatives, the people I work with, people I see all the time. There are other kinds of social interactions that go on, right? There are social norms of behavior, right? And so, for example, there are things that some of you won't do in this room simply because it is not normative to do so. I'm going to tell you a story about this. A couple of years ago, there was a student actually in one of these programs that we've been doing for some years now, and we were talking after a session, and she was rubbing her back, and I asked her if she was okay. And she said, no, I have back problems, and this is really a very long time to sit. And I said, well, why didn't you just stand up? Because I know that that sometimes just standing up and, kind of relieves your back problems. She said, well, if I stood up, everybody would look at me, right? There's a social norm about behavior in classrooms, right? And that it's something that is distinct, right, from a peer effect. After all of you have come from very different places to be together. It's not like you have long-standing connections of any kind. Some of you probably do, right? But many of you don't, and yet there are norms that you have grown up with, right? That essentially are governing these behaviors. This is another kind of social interaction that is very important and connects with the kinds of peer influences that we're going to be talking about today, but really is a bit distinct. And so there's a lot to read about that. If you want to talk about trust, one question to ask is, how do we move from trust as a peer-to-peer interaction to trust as a social norm, right? This is the move from particular to generalized trust, okay? Where do we see social interactions? Where are these peer effects important, and where have they been studied in the economics literature as opposed to other literatures? Well, in labor markets, for example, peer effects are obviously important both for for at one end, at the beginning end of your work life, what career choice do you make? What kind of jobs do you choose to look for? At the other end, when do you retire, right? What do you do when you retire? Fertility, customs and peer effects around childbearing, right? I have a former student who, in fact, is a Bedouin who lives in Israel, and he had, when he was a student, he and his wife had, I believe, 1, 2, 3 children, okay, and she had said that's enough, and then at the end of his graduate school, he got a job in Israel, and he moved back actually to his home village. And within 2 years, within 3 years, there were 2 more children. Why? Because of the social pressure to have children, right? And that again, right, she was stigmatized for not having enough children. You didn't want to be the smallest family in the village, right? And if everybody feels that way, you can imagine what family sizes are going to be like, okay? Educational outcomes, right? We all are influenced in our classrooms by the behavior of our peers, both in how they set standards for us on the one hand, and on the other hand, how we can learn from each other, right? And we often do. So these are different kinds of things. An interesting application of thinking about these social interaction models that we're going to be talking about has to do with violence. Things like revolution, or even just things like crime waves and stuff like that. We'll talk about this a little bit, right? How does crime beget more crime, all right? So in any event, I've also listed here a number of different mechanisms on the other side here that talk about how social interactions might be felt. Peer effects is one, just, you know, the pressure of your friends. You don't want to be stigmatized by your friends from being too different from them. Role models. There are people that we look up to, right? And the people that we look up to, if you think about it, this is something that's often manipulated. We learn in school, for example, to look up to certain people. This is the person we should emulate when we grow up, right? Or our parents might point us to particular people and say, be like him, be like her, right? So role models, social norms, we've already mentioned. Social learning, I've mentioned this rather briefly. We're going to be talking at some length about a couple of papers having to do with social learning. This has to do with learning from the experiences of others, right? You've all in microtheory classes studied Bayesian learning, where we have individuals who go out and collect information, and then based on this information, in a world of uncertainty, they update their beliefs and then choose so as to maximize expected utility or something like that. Well, what happens when I'm learning not just from my own information, but from the information of others, right? What happens when there's a strategic component to that, okay? So that maybe I'm learning from you, but maybe we're competing. Or on the other hand, maybe we're cooperating, and how might that play a role? These are all important questions. Social capital. Social capital is a phrase that one hears a lot, okay? And the first problem in talking about social capital is, what is social capital? But I think many people understand this as the kind of collection of informal social institutions that sustain the various interactions, and in particular market interactions that we are involved with. There are many sharper definitions than that, and I'm just going to leave it there. And having kind of talked about social interactions in general, let me talk a little bit about how we might study them. Now, in economics, as you know, mostly what we do is we get data sets and we apply all kinds of econometric techniques to them, right? And it used to be the case in economics that if we didn't have real-life observational data, there was no point in looking at the data. Doing surveys, why would you ask people what they want to do or what they would do? Right? Who knows what that could mean? But if we actually see them do it, right, then we know. So you shouldn't ask people, what will you demand if you have this much income and the price is that? Instead, you should do revealed preference. okay? And this was a very common attitude in the 60s and 70s and all of that. Now, of course, but if you want to study social interactions, however, you need much richer data, and you're going to not find a lot of this observational data that I've just described that is going to really speak to the problems that you're going to want to look at. So people I know who work in this area, myself included, spend a lot of time reading ethnographies, right, where we have anthropologists or sociologists who go out and live in a community and kind of write descriptively about what goes on, about how things work. We have field experiments so you all know about experimental economics, right? How many of you are interested in experimental economics? One? Only one? Oh, come on. I don't believe that for a minute. How many of you are interested in behavioral economics more generally? Really? You're the one at the forefront here. So this is a surprise. Usually when I ask that question, even among predecessors in your group, like about a third of the hands would go up, right? So, so it's not you, it's them, okay? You got it, all right. So it's one thing to do experiments in a lab, but it's another thing to actually do. The problem with laboratory experiments is that people go into a lab and they do something, but it's not anything like a real life experiment. So there's a question about how just because an economist says that this experiment is meant to model this real world phenomenon out there, this real world experience, it doesn't mean that the subjects make that connection. And if the subjects don't make that connection, then whatever you see revealed in the lab is not going to actually say very much about what the economist thinks the laboratory experiment is modeled, right? This is a big issue. So one way around this, right, is to go out into the field, to actually go to places where people live and work, right, and design experiments that make use of their experiences, make use of the kinds of things that they do every way. This is a way of controlling the context of the experiment, right? Now, whether or not you can actually succeed at doing this is really an open question. Some people say yes, some people say no, but this is another approach. Then there are large-scale experiments, and there are really two kinds of large-scale experiments. Every time the government changes some policy, what they're doing is performing an experiment, right? And sometimes that change in policy is sufficiently clean, okay, sufficiently unconfounded by other kinds of things that we can actually learn a lot about behavior just by studying, the before and after of the policy change, okay? Or places where the policy has changed compared to places where the policy hasn't changed, okay? So now we're actually looking at experiments that are essentially provided to us by the government or forces of nature or something like that. It's also been done in many circumstances that large-scale social policies have actually been instituted in part with the idea of actually studying things. So for example, in the United States in the 1970s, there were experiments with negative income taxes. And these were, these experiments were basically done at the state level, right? So this is a very large pool. There have been a number of experiments that have been done, for example, with public utility pricing, right? Where you get the public utility to actually change the price of energy for significant groups of its consumers, right? And this has also been done in the United States. And so these large-scale experiments are occasionally done. But what I want to mention is that especially in these first two areas now, in these first two methods, we're bringing things into economics that would not really have been done very much 20 or 30 or 40 years ago. Well, certainly not 40 years ago, probably not even very much 20 years ago. And the best work is kind of paying attention to this and using this to inform the econometrics that we see. What kind of questions do people who study social interactions ask? We ask questions about, as I said, about social norms, about group membership, about peer effects, and in particular in studying peer effects, there are two different kinds of things that we want to look at, okay? We want to study things at a very micro level. If we think about, for example, social learning, I want to actually ask the question about what is it that people learn from their neighbors, right? How wide is the scope, right, of the, how large, rather, is the set of people from which they might be learning? And a bunch of micro-level questions like that. On the other hand, I also want to ask questions about the aggregate effects of social interaction. So, for example, will I see, for example, if I can, that because of social learning, will I see, in fact, that there will be an increased uptake of a new variety of a crop relative to what was going on before? Does social learning magnify adoption of new technologies, or does it retard it? Or what is the role of social learning in de-adoption of technologies? Okay, these are aggregate questions, and of course, what we want to do, you know, we want to actually look at both kinds of things. There's a name that one often hears associated with these aggregate questions. When we write down a model, for example, of a bunch of farmers in villages learning from their neighbors about adopting new crops, the level of description is to build game theoretic models, for instance, of the behavior of the distinct individuals with respect, where we model their choices and see how their choices are determined by the kinds of information they get, and so on and so forth. So all essentially the equations which drive the system are going to be equations that says that individual I does this and individual J does that. Those are the kinds of things we look at. On the other hand, when we ask questions like, okay, what is the rate of uptake of this new technology, right? Well, that's at a different level of aggregation, right, than the equations which drive the system, okay? So we call these kinds of things emergent properties of the system, okay? And emergent properties of the system are properties which exist on a time scale or a spatial scale which is different from the scale at which the drivers of the system actually operate. So in social learning, the drivers of the system are actually at the individual level, but the adoption rate is a global thing, okay? And we want to study the effects of the local on the global, because why? We might want to, for example, see if we can influence social learning by maybe redesigning some agricultural extension programs or something like that, or identifying in villages particularly successful farmers and encouraging them to adopt a new technology or a new crop in order to, so that their success will be visible and other individuals in the village can see it and then take it up, right? So there are policy questions here that we will want to study. Yes?
In some sense, now you actually try to investigate the mechanisms why you actually can have spillover effect, right? And providing explanations for that, right? Other than other channels, the channels why you have spillover effects.
Well, you know, I think the spillover effects happen at the local level, right? But the consequences are global. And so let's go back to technology, for instance, for a moment. So it used to be the case, well, it still is the case, that people talk about technology adoption in terms of these S-shaped curves, right? And they say this curve describes, right, the rate at which things are taken up. And then they estimate it in various different data sets by looking at the percentage of people as a function of time, or the percentage of people as a function of the number of current adoptees who adopt in the next person. And they estimate this kind of thing, right? And then they have some difference equation that says that xt plus 1, the number of people who adopted at x, the stock of adoptees at xt plus 1 is f of xt, where xt is the number or the stock of adoptees at period t. And so they're just going to study this at an aggregate level. But what we might want to do is to say, well, where does that curve come from, and how can we change the shape of that curve? And we do that at a micro level by studying the micro process. Not sure that that really responds to...
No, yeah, I think that actually is what I'm thinking. Is now we do observe that the spillover effect, and then also affecting the aggregate level
Right.
shape that we have.
Right.
And the one thing that we are providing right now is from the micro level, having this social interactions to explain
Right.
why technology is like that.
Right, that's right, that's right. This is like, the minute you move from atoms to molecules, stuff gets more interesting. Right, it's exactly that. Okay. So I want to give some examples. I want to talk about this property of local versus global, okay? Of micro level versus emergent properties of the system. So to talk about a very nice example, there is a paper by Tim Conley and Chris Udry, which appeared in the American Economic Review in 2010. And I was stupid enough not to put the title on the slide, and I don't remember it at the minute. Moreover, this is not yet in the bibliography. My notes, which will be posted, right, conclude with a large bibliography, but I just changed this morning when I discovered I was going to be speaking. By the way, if I actually die while I'm up here, don't be alarmed. Maybe be a little alarmed, but not too alarmed. I just flew in yesterday, and I didn't expect to speak until the end of the week, and I'm really pretty jet lagged, and I have no idea what I'm saying even now. Okay, which is another reason to ask lots of questions and interrupt me. Say things like, "Did you really mean that?" Okay, that'd be a good thing. Tim and Chris wrote this paper, and the issue actually was they wanted to study how it is exactly that farmers begin to adopt new technologies, new ways of doing things. As you can imagine, that there was a large literature on this, a large pre-existing literature into which they're writing. We can think about how farmers learn. Farmers learn by their own experience. Farmers learn because people from various kinds of extension programs come out and show them stuff, right? Things like this, that there's training, there's media presentations and things like this, right? That there's articles in newspapers and stuff. And then there's also social learning, by learning what's happening with your neighbors and seeing what they're doing. And what Tim and Chris wanted to do was to study this third channel and understand really how important it was, or how important it is, okay? And so they, the standard literature basically, and there's a number of papers here that study learning. Okay, theirs was not the first paper to study learning the adoption of new technologies. And again, I'm sorry, I don't have the references very carefully. There will be, by the time the slide, we'll post a final version of the slides later that will have all of this stuff. And I will try and do that tonight if someone will give me some toothpicks to keep my eyes open. And then we'll have everything up to date here. But in this traditional literature, if I can call it that, although it's really not that old a literature, we think of the village, a typical village. So we're going to imagine that we have a country and it's divided into little villages. Sound familiar? Right? And so the village itself is a learning unit. Some farmers experiment. Other farmers do not experiment, right? But every farmer in the village observes the farming activities of everybody else in the village, and then they get some idea of what's going on. They then update their own opinion regarding the technology. They update their beliefs in some way. This is all sounding very familiar to you, right? So are you all thinking like good Bayesians here? They're computing posterior beliefs about the effectiveness of the new technology, right? And they're doing expected utility maximization. Are we all on board, right? Okay. And then they make decisions with this decision rule regarding cultivation for the next season. So this is the standard story, okay? And a number of very good papers have been written that have explored this. I know, but I have a set of, this is part of my confusion, not really being prepared to talk today. I also have a set of slides with speaking notes, and I forgot to tell you what it is that we are talking about here. So let me actually find that. Just give me 1 second. Okay. So the story here is the following. This is what Chris and Tim wanted to study. And maybe I should even move this to a place where I can see it, which might be here. Okay. Okay. So over the past decade, this paper was written. Actually, this paper was written a very long time ago, but it was published in 2010. But in the late 1990s, in part of the eastern region of Ghana, in Africa, you all know Ghana, okay? An established system of farming for local consumption, maize and cassava. Cassava is a fruit. Maize, you know, maize is a corn-like thing. Had begun to be replaced by a new crop, pineapples for export to European markets. Okay, so we have a new crop coming in, and of course there's going to be new technologies associated with this new crop. So you have to, if you want to participate in this, you, formerly producing maize and cassava, now have to learn about how you produce pineapples. Okay. And you have to figure out whether it's something you're going to do. Now, an important component of this transformation is the adoption of agricultural chemicals that were not used in the previous farming system. My understanding, I've never been to Ghana, but I have actually marched around East Africa a little bit. You know, it's true that you get more production if you use fertilizer, but a lot of people can't afford fertilizer, and so if they're lucky, they have access to a cow, and that provides some natural fertilizer, and otherwise you make do without. Pineapple really needs some experience with a different set of chemicals. So what Tim and Chris wanted to do was to understand about how farmers might learn the appropriate use of these new chemicals. Okay, so a survey. So I've just described for you. Let me go back briefly and mention. Okay, let's remember the basic model. We have these villages. Everybody in the village learns from the experience of everybody else, right? And this is going to give us some kind of adoption profile that is going to be this S-shaped kind of thing. And now the question is this really the right model? Does this really describe the microeconomics of what's going on? No doubt, if you put enough parameters into the prior beliefs, if you put enough parameters into the utility function, you can tune this sucker to get whatever adoption curves you want, right? But that's not necessarily a very helpful thing to do, because remember the experiment. What is it that we do in economics all the time, right? I'm pausing for an answer. I know I'm not going to get an answer. What we engage in is counterfactual thinking, right? We're going to ask, what happens if we change this, if we change that, right? And taking a bad model and tuning it so that we replicate the current environment doesn't mean that it's going to predict well out of sample. By which I mean it may not necessarily, probably will not predict well when we change some important variable that we might be able to manipulate by policy. So even though we can match the curve with the simple kind of model like this, the adoption curve, it doesn't mean that we're going to know what happens to the adoption curve when we change important parameters in some way. And that's really what we're after. And in order to learn that, you have to go down to the micro level and see how it is that people are actually learning. That's why we do this, okay? All right. That actually might be kind of the single most important level. You've got to build structural models, or have in your head structural models of what's going on in order to talk about policy analysis. And we're going to be learning a lot more about that when Xiaofu talks about labor markets, and in particular when Chris Tabor talks about the econometrics of policy analysis, and we'll see how this works. Okay. All right, so now that we've recalled this, let us move right along. So what did Tim and Chris do? They looked at a survey of approximately 450 individuals in a bunch of villages in Ghana's eastern regions over a period, blah, blah, blah. You can read this, okay? And they got really good data. They had plot-level data on inputs and outputs, which they got rather frequently. They also got a variety of data from farmers on things like who they talked to, right? And what they learned from those people they talk to, right? Do I actually know, for example, how much fertilizer you used, or do I know that you used a lot versus a little? Those kinds of things, okay? So it's pretty detailed data, right? More than most of us ever get to see. Now, what about the story? What about the story that we told about the village as a learning unit, right? So one way, here's how they actually looked at that. One thing they did was they just randomly matched each farmer with 10 other farmers in his or her village. And now the question is, well, you know, who among these randomly 10 people that we chose did you talk to? If the village as a learning unit is correct, right? If that model, village as a learning unit model, is correct, you should have spoken to probably most of these people, right? But in fact, what they found was that only 11% of the matches had any one of the two individuals in the match ever received advice from the other guy, right? Basically, there wasn't a lot of talk going on. In only about 30% of the matches did one farmer say, I could even ask this other individual about farming stuff, okay? And then when you went down to a more detailed level and asked, well, you know, what can you tell me quantitatively about what this guy did, what that guy did, what this other person did? It turned out that the likelihood that any one individual would actually know the answer to those questions was really, really small, okay? So this data collectively basically rejects the village as a learning unit story. Basically, people are not talking to everybody else in the village and not learning from the experience of the village as a whole. Instead, what's happening is that information is flowing through a sparse local network. Instead of everybody talking to everybody, everybody is talking to only a few other people, okay? So here, for example, is a graph where this is the network of information flows in some rather small village that is in their study, and you can really see that it's small. Every circle represents an individual, okay? Every line represents a connection where somebody was talking to somebody else, okay? If the village as a learning unit model story was correct, every circle would be connected to nearly every other circle. The graph would be very dense, right? But you can see here, right, that that's not the case, that the graph is really rather sparse. For example, for this guy to reach this guy, look at how long the path is. This guy would have to talk to this guy, who talks 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 to this guy, and finally, whew, okay, right? That's what I mean by rather sparse. Now, this graph was actually drawn in such a way that we can also see that you don't necessarily talk to your nearest neighbors, okay? So the graph is actually kind of plotted geographically so that, and that's why we have this kilometer scale here. So you can ask, well, how far? This guy like really lives out of town, right? And who does he talk to? People who live rather far away from him. Maybe their soil conditions are kind of different, right? And on the other hand, here, you know, we have a dense group of people who live close to each other and talk to each other more. And one question asks is, well, how important is that? Okay. And all right. So in any event, this is the micro story of what's going on. Now, how did they study this? They studied this by actually just thinking about a very simple production model where you put in your inputs at time t and outputs come out at time t plus 1. I'm not going to describe this in any detail. As soon as I give you the details of the paper, you can read the paper for yourself, okay? Production is determined both by the amount of fertilizer that you use and a random shock. Shocks are IID draws in their model from a common and unknown distribution. That's not necessarily a good assumption. We might want to assume, in fact, that there's some kind of spatial stuff going on, that your soil is different from mine. and maybe therefore shocks should be correlated but not necessarily drawn from the same distributions. They shouldn't be, they shouldn't have this common structure. Farmers are Bayesians. And what did these guys do? They did two different things. They first considered two different regimes of information transmission. Knowing the social network in these different villages that they studied, they wanted to ask first, well, what would be the effect if they had more communication amongst each other? In other words, if more people were connected in the network, that's one question. A second question is, one of the things they found was that people tend to know stuff on the order of, well, this guy used a lot of fertilizer, that guy didn't use a lot of fertilizer, but they don't really know quantities. They don't know the details, right? What happens if people were encouraged to share more of the details? So this is, what are they actually doing here? They actually looked at both of these regimes. Another thing they did, and I think this is something that's very cool, is that they could go back and also look at the time that some people were doing these pineapples. Other people, of course, were still sticking with maize and cassava. Everybody knew how to grow maize and cassava, right? So one of the ways of detecting social learning was to compare to use this model and estimate the importance of communication and information in the pineapple world, and then to estimate the same model in the maize and cassava world, right? And you would expect to find that if social learning were important, you would see the learning parameters would be significant in the pineapple world, but not in the maize and cassava data analysis. And this is, in fact, what turned out to be the case. Otherwise, the paper would not have been in the AER, and I wouldn't be talking about it. All right. Okay. Here's the conclusion from the paper. It's a lot of stuff to read. This is actually a quote from the conclusion of the paper. And what do we learn from this? Is that some information is more important than other information. Some information is used, other information is not used. They worried about things like credit shocks, because if you want, the problem is if you have to buy fertilizer at the beginning of the season and you're only going to get the revenue at the end of the season, you're going to need some kind of liquidity in order to be able to get the fertilizer at the outset. So they worried about credit markets and things like that and controlled that. They found, for instance, that it is new farmers that were most responsive to new information. That is consistent with the learning story, right? Guys who already have a lot of experience, it's going to be harder to move their posterior beliefs. You all agree with this, right? And so they're not going to be as responsive. And as I said, when you compare the learning evidence, the evidence in favor of learning, the evidence that is interpreted as favor of learning for maize and cassava versus pineapples, you see that maize and cassava does not a lot of evidence that learning is going on, whereas in the pineapple world it is. So this is an example of a micro-level study. I want to go back, not there, I want to go back over here to this picture, and just think for a moment about how hard it is to actually, what kind of model makes sense for thinking about this, okay? If everybody in the village were talking to everybody else in the village, right? And if we go with this assumption that everybody is getting hit by an IID shock, okay? And so the basic story is that there is some parameter which is important, right, for pineapple production. No one knows this parameter, right? And this parameter describes the distribution of shocks. So what you want to know is whether there's going to be a lot of bad shocks or a lot of good shocks, right? And that means you want to know like where the mean of the distribution is, and you don't know this, okay? And if you were experimenting on your own, if you were a lone guy, you just plant and you'd get a reading 1 year and you'd plant and then you see what happens the next year. And over time, you would accumulate a lot of data. These are all IID draws, IID across time, right? And gradually your posterior beliefs would converge and you would become confident about where the mean is. And at some point, you might stop and switch back to maize and cassava, or maybe you would stay on. Right? This itself, by the way, is a very interesting problem, right? How many of you have heard of things called bandit problems? Right? None of you. You have. Who else has? Hands. No one? Okay, bandit problems are very interesting things, okay? Here's the canonical bandit problem. You've got pineapple. You don't know anything about growing pineapple. You have maize and cassava. It too is random, but you know the distribution for what's going to go on, okay? So what are you going to do? You're going to start experimenting with pineapple and all that. But if you get enough bad draws, you're going to say, oh, the heck with this. I'm going back to what I know, to maize and cassava, right? But of course, it may be that you just got a bunch of bad draws, and it really is that pineapple is the better deal, okay? But once you switch out of pineapple, you know, your beliefs aren't changing because you're not getting any new data. And since you're not getting any new data, you're just staying where you are and staying where you are. And so you're effectively done and you're locked into a bad choice, okay? And this is something called the bandit problem, right? And it's often alleged that, well, maybe social learning mitigates the bandit problem to some degree because maybe you're not learning from your experience because you're stuck in maize and cassava, but this other guy over there is doing pineapple, and you can get evidence from him even when you're not getting evidence on your own. So even though you might have switched out of pineapple to maize and cassava, you may come back, okay? But now I want to think about how complicated the learning problem is. If everybody is talking to everybody else, instead of getting one IID draw every period, you're getting a bunch of IID draws every period. Okay, and you just do the updating with K instead of N, K instead of one new pieces of data, where K is the number of people in the village. And that actually is very straightforward, okay? But I want you to think now about the learning problem that this fellow right here faces. So he does his experiment, and this guy up here does his experiment, okay? And maybe we've got a group of people around here experimenting. So this guy, right, in the next period knows what happened to this guy, right? He sees this guy's choice, right? He knows what this guy did. That's fine. But in the next period, the following period, what happens? He gets some new data from this guy, but this new data from this guy, right, kind of incorporates what happened to this fellow, right? So just as after period 1, this person learned from this guy here learned from this guy, and now we expect that information to be transmitted in period 2. Now, write down the likelihood function for that, right? Doesn't it seem like Bayesian updating is going to be really complicated? Okay. Not only is it going to be hard to actually model that, it might even give you belief that maybe people aren't really going to be very good Bayesians. And so we might want to look at a lot of non-Bayesian learning models instead, all right? But if we do that, of course, then we're doing something very, then we've left the domain of rationality. Is that a problem for anybody in this room? No? Okay. It's not for our one behavioral economist, but the rest of you guys could be, right? Okay, so the point is that these learning models get very, very complicated very quickly, and we might want to consider all kinds of it. We have to take kind of our behavior. We have to really examine our behavioral stories very carefully when we do this. All right, so this is enough about technology adoption, and we've seen things about how things work at the micro level. Now I want to talk about things at the aggregative level. 1996, Ed Glazer, Bruce Sacerdote, and Jose Schenkman write a paper on crime. There's something very puzzling about crime data in the United States. By crime data, I mean, what is the incidence of crime? If you get, say, city-level data on crime for the large metropolitan areas of the United States, the first thing you might begin to do is you would look at the crime rate for every city, and then you would want to correlate this in some way with all kinds of descriptions of the city. For example, median income, right? all kinds of, all kinds of other, the amount spent on police, right? So on and so forth, all right? And once you control for everything in sight, the striking fact is that there is a lot of residual variance. You haven't really explained very much. So the question is, if you really thought, for example, that crime was kind of an IID phenomena, you decide to commit a crime, you decide not to commit a crime. Valerie back there says, oh, I'm a criminal, just to pick on you. All of that, then maybe we would expect to see smaller variances than what we actually see in the population, okay? But actually what we see in cities, okay? So again, if based on conditions everybody is making an IID decision, we can actually compute, right? What the distribution of crime should be in city 1 and what the distribution of crime should be in city 2. We would see the means for each city. We would also see the variance for each city, right? And then we can actually kind of look across cities and see how much variance there is across cities after we've controlled for all of their characteristics. And the point is that there's a large amount of variance left, larger than an IID model might lead you to believe. So Schenkman at Glaser et al. Had the following idea. He said there must be some positive covariance across agents' decisions, that somehow my decision to commit a crime, right, might affect your decision to commit a crime. The crime is a group phenomena. Yes, a question, thank you. Yes.
Does the high variance mean that it's at tell or just the variance is high?
All right, well, that's a good question. I think, as I recall, when they did this study, they were assuming normal distributions throughout, so there's no possibility for a fat tail.
Whether you compare to the standard normal or something?
Well, no, but I mean the point is that even in the normal distribution is a 2-parameter distribution, right? It has a mean and it has a variance, right? And it's just that second parameter is large, okay? Whereas now, if I had fat tail distributions, I might wonder about, well, is the variance even finite, right? Because if the tail is thick enough, the variance, the second moment won't exist, right?
So the larger is compared to the mean.
So what I mean when I say is that I can do a calculation, right, based on IID crime rates for IID probabilities of committing crimes for individuals controlling for stuff, and then I can get a variance in the city crime rate, right? Or the amount of criminal activity in the city, and I can look at that in time series, right? And then what I would find is that now looking across cities, that there's a huge amount of variation in that, right? So the mean in this city is going to be very different than the mean in that city, even after we've controlled for everything. That's what I'm talking about. But I can pose that in the standard norm. I can pose that in the normal world, okay? Now another question to ask is, is there really kind of a power law phenomena of some kind going on? I think that somebody is going to shoot me for saying this. I wish this weren't being recorded. I suspect that the number of cities in the United States is sufficient, of a reasonable size, such that you could group them together and say that similar things are going on here as there. I think that number is sufficiently small that it's not meaningful to talk about what the tail looks like. Okay? I mean, power laws are very compelling when we have very, very large numbers, right? So when we talk about the income distribution for a country, right? But if we talk about the income distribution among 30 people, right, who knows, right? So, so I'm not sure that that the restriction to, well, you'll see. This is a very kind of off-the-cuff analysis. This paper was published in the QJE. Okay, that tells you a lot about the paper. But it's a very innovative paper, right? Why is it an innovative paper? They said, what are they doing here? They're saying, maybe our understanding of the microeconomics of individual criminal behavior is not what we think it is, and that has an impact on this emergent phenomena, namely cross-city crime rate variations. right? That's the big innovation in the paper. And that was a huge innovation in 1996, right? The fact that it wouldn't be today just tells you that we've really taken that up. So here is a very simplified model to illustrate the phenomena that they want to talk about. And this is actually in the paper. They said, let's imagine a large city and everybody is lined up and everybody looks to their right, okay? Actually, I want to have everybody look. Actually, what I want to do is I want to have everybody looking to their left, okay? So that, and we're going to talk about a pure effect. Here's how the pure effect is going to work. We're going to have some people who are hardened criminal types. They just commit crimes. They don't care about anything, okay? Then we have other individuals who are good guys, okay? They never commit a crime. They're just naturally good people. That's all of us, right? Okay. And then we've got another group of people, maybe the largest group, and they are people who are swayed by their environment, okay? And that's going to be our type 3s, right? And everybody looks to the left. And I've got to have someone on my left, you're going to be on my left, I am looking at you. And I am one of these people in the middle. I'm not a good guy, I'm not a bad guy, I can be swayed. If you're doing criminal activity, then I'm going to do criminal activity. I'm going to imitate you. If you're not doing criminal activity, then I'm not going to imitate you. I said the wrong thing. This is my jet lag. If you're not doing criminal activity, then I'm not going to do criminal activity either. Okay? So you have this influence on me. I am on your left, you're looking at me, and you're taking your cue from me. He, on the other hand, is a hardened guy, one way or the other. He's either a good guy or a criminal guy. This chain ends. Okay? So now I've described a model that's going to have a lot of correlation, right? So how is that correlation going to work? Here we have a criminal guy, right? Reds are going to be bad, blues are going to be good, okay? And blacks are going to be influenceable, okay? So in the IID world, we'd have some probability that this person is going to commit a crime. We'd have some probability here that this person would commit a crime, so on and so forth. In the world I've just described, this person is, pardon?
Why the individual only look at the guy in the left side, not the right?
Because it's easier for the calculation. Okay, that is exactly the answer. I'm not making fun, right? They actually have an appendix where they do this for both the left and the right. And you might say, well, why are we doing a line? Because I don't know any cities that are just a line, right? But this is illustrative. What they wanted to do was to provide an illustrative model to show how the variance can blow up, all right? And we're going to do the calculations on the next slide to see how the variance is going to blow up, even in this world, right? And yeah, it might be a little more compelling, to actually see this for a general graph, but which you could do with great pain. But I think the minute you see this story, you're going to find it convincing and it's going to suggest some stuff you can do with the data. All right, so the story is basically this. Now what's going to happen is that we're going to see these long chains. So this is going to be a chain of 3 that are criminals. Now we're going to have some chain out here of good guys. And we're going to keep going, good guy, good guy, good guy, till we hit the next hardened criminal. And then we're going to have a chain of criminals and so on and so forth. So now what we're doing is we're creating a great deal of correlation. Okay? Everybody understand?
Another question. The distribution of these guys, who is good guy or who is bad guy, is that exogenous?
So I haven't said that yet, and I'm going to describe that on the very next slide. Okay? So what I'm going to do is I am going to, yes. I'm going to assume that P0 is the probability, I don't know which way I did this, is the probability that somebody is a good guy. And P1 is the probability that somebody is a bad guy. And 1 minus the quantity P1 plus P2 is the probability that someone is influenceable. Okay? So pi is the probability that a person is a committed type. Okay? All right? So if I take a random, if I take an individual, and I want to figure out what is his expected value? What is he doing in expectation? What I would do is I would just walk the chain backwards to the first committed guy, okay? And then I would say, well, what is that committed guy doing, okay? Well, conditional on being committed, the guy is a criminal with probability P, right? What is this? This is the probability of being a criminal given that you are either a criminal or a good guy, okay? All right, and so what I'm doing is I'm just walking the chain backwards until I get to a hardened type, okay? What I want to look at is the total amount of criminal activity, okay? And now what we're going to have to do is we're going to have to take account of the fact that these chains have some length. And the smaller is pi, the longer is the chain, okay? And so therefore, if one person flips, a hardened type flips from being criminal to being good, a whole bunch of people are going to flip, okay? So we should expect to see higher variance. So what we can show is that if we look at this number Sn, 2n plus 1, because we've got n people over there, and one person in the middle, 2n plus 1, right? So this is, in some sense, the average crime rate, okay? Normalized to 0. Right? I mean, this is, minus the mean, right? So we're interested, this converges, this actually converges to 0. That's not hard to see. And this thing here, right? This is, so there's good, now we want to see what does the central limit theorem have to say. And when we multiply by the square root, right? So in other words, we're taking this and we're dividing this by the square root. We are going to have a limit distribution, which is going to have 0 mean, no surprise. It's going to have some variance. What is that variance? That variance is the variance that you would expect to see if everybody were IID, but it's now going to be magnified by the chain effect, right? And if you do the calculation, and you can do this on your own or you can read it in the paper, the variance is greater, the smaller is pi. And of course, the smaller is pi, the larger the chains, okay? So now what we see is the effect of the social interaction is to introduce more variance here, okay? I didn't do the math here because it's tedious. And I always find that looking at math on slides doesn't tell me anything because I can't absorb it in the 30 seconds the slide is going to be in front of me, but it is in the paper. It's also a good exercise to do on you. It's within reach of everybody in this room. I promise you, okay? All right. So having done that, they then go and they then estimate this. And I'm not going to talk about the estimates, okay? But what they find is basically that, that you can use this effect, right? You can measure scaling. I mean, you can ask how much bigger is the variance than what you would expect to see in the IID story. And then from that, using that formula, you can back out pi. And you can make some adjustments for some other stuff that they do here. And then you can see that the estimated multiplier effect for different data sets that come from criminal activity is really pretty large, okay? So they claim that, what they're claiming is that there's a lot of not serial correlation, but a lot of cross-individual correlation in decision, there's a lot of cross-individual correlation in individual decision-making, and that the aggregate effect of this is it blows up the variance in crime rates, okay? And so this is an example of an emergent property, right, that is driven by a social interaction phenomenon, all right? By social interaction, namely imitation of criminal activity. Now, you can get into finer studies about, the criminologists will tell you, for example, that they have a lot of micro studies that talk about is there, what is the nature of the social interaction? Is there a lot of imitation? Or are there just common factors that are affecting people, right? And that's a hard thing to untangle. Most criminologists will tell you that while the answer to that question for adults is ambiguous, I believe, they would say that. They would say that the evidence is very strong that if you look at crime among younger people, that there's a great deal of serial correlation. And this has been studied a lot, and a lot of details about how this actually works have been reported. And I think there's a small bibliography on this in the notes for those of you who are interested in criminal activity.
So if you allow for segregation or allow for people to choose where they live,
Pardon me?
if you allow them to sort of not linear cities, you instead actually allow them to sort of choose where they're going to live and who they're going to interact with, that possibly
Well, this brings up actually the third point on this slide. All right, so let me talk about that. How are we going to actually test for these kinds of peer effects? Right, there are a number of problems that present themselves. Okay, one is the problem of unobserved correlated shocks. Okay, so there's remember this name Sacerdote from the crime. He also actually wrote a paper. It's a nice example, actually, of a experiment that is provided to us at Dartmouth. Who went to Dartmouth, right? You were at Dartmouth, right? Oh, New Hampshire. Okay, so at Dartmouth and at a number of other American universities. You know, at American universities, at many American universities, including all of the better ones, most students actually do not come from the area. Right? And so they come to the town and they live in dormitories that are provided by the university, okay? And of course the idea is, we want to pack a lot of students into a room, typically 2 to a room or maybe 3, but 2 is a better idea, and provide them some housing, okay? And this is all done by a university housing operation. And some universities, including Dartmouth University, where Bruce is on the faculty, roommate assignments are random. Okay, and so what they did, what Bruce and co-authors did, was to actually look and see whether there was correlation in the performance of roommates, right, during the academic year, right? If you were a good student in your first year when your roommate assignment was random, was your roommate, your randomly assigned roommate, was he or she also a good student? Okay. And if so, you might think that that would be evidence for some kind of peer effect. Each of you are kind of egging on the other or providing an environment where the other person can study or so on and so forth. Okay. Well, there's a lot of, but that, there's not necessarily a peer effect there. So for example, it might be that you and I are roommates, okay, and we are not doing very well. It turns out that we're both pretty studious people, but the problem is that we live right next to these guys who are playing the stereo all night long, right? And we just can't study, right? Okay? That is an unobserved correlated effect. There is an epsilon that has hit both of us, okay? And so one of the things that we have to distinguish is there a real peer effect, right? Or is it just due to a correlated error? That's a hard thing to do. Some people say that's the hardest thing to do. Another empirical problem is knowing what the network is, all right? In the roommate thing, it's really easy because the university just assigned these roommates at random, okay? In Ghana, somebody actually went into these villages and talked to them. There's a more recent research that has been done by Esther Duflo and Matt Jackson about villages in India. And again, a lot of enumerators went out into the field and they went to people and they said, who do you talk to in your village? And they actually collected network data, okay? But, there aren't really you can count, probably by now it takes 2 hands, but not a third hand, you can count how much data there is like that. Endogeneity of the network. This is exactly your problem, right? Maybe what happens is that good guys move in together. Maybe you say, I don't want to live in this criminal neighborhood, right? And so the location of people, of types in the Glaser, Sacerdote, and Schenkman story is not IID. Maybe, in fact, that good guys, that hardened good, that preset good types and preset bad types cluster together. Right? And that would have implications for the story. In fact, what it would probably do is reduce the variance, although we have to figure out how that exactly worked. Another problem that we're going to talk about later maybe is distinguishing endogenous and contextual effects. So the problem is the following, that if you and I behave in similar ways, okay, it may well be, there's some covariate that affects your behavior, and then that is transmitted to me through the peer effect, right? And so we get this correlation, right? Alternatively, this covariate, which affects you, also affects me, okay? And because it affects me, right, then I get the same kind of outcome, even though we are not, in fact, it's not a pure effect. So for example, suppose that we look at classroom level data on educational outcomes. And we have, what individuals in this class did, what individuals in that class did. And we make an assumption that's very similar to the village learning model story, right? Which is to say that everybody in the class is connected to everybody else, okay? Now having a good teacher, right? Suppose that I can observe teacher quality. Well, that is a contextual effect. It affects you because you're in the same classroom as me. It also affects me, but you're in a different classroom, and so it affects you differently, okay? So sorting these things out, and there's a name for that problem. It is referred to in the literature as the reflection problem. I believe it is a largely non-existent problem and have written 2 papers to prove it, but it is something that both of them with Durloff, right, actually. But it might be, but it is something that people do worry a lot about, for better or worse, and something you should be aware of. So these are empirical issues in taking this stuff to data. Okay. Let me see what I want to say here. Okay. This business about the endogeneity of the network, I think, is really critical. And different versions of the story actually give rise to different social problems. So, for example, we might imagine that networks evolve around the behavior of neighbors. So you might be interested, for example, in studying drug abuse, right? And what you might find is that people who use drugs, right, are in fact recreational pharmaceuticals. You know what I mean? Okay. It might well be that people who engage in the use of recreational pharmaceuticals, in fact, have among their peers a higher percentage of other people using recreational pharmaceuticals than those who do not use drugs. Okay. All right. Make sense? All right. So now the question is why? Well, one possibility is that drug users find each other, okay? That's the effect you're worrying about. The network is endogenous, right? And drug users find each other. People cluster together based on their behavior. The bad news for this is that what it means is that these drug users then become socially isolated, and they reinforce themselves, right, by forming these networks that basically reinforce the behavior they have, right? And so we get social isolation as an outcome of this, and consequently, higher levels of drug use. We get a social magnifier effect. The other thing that could happen is that we have behaviors basically evolving around networks. Okay? Yes?
Yeah, I'm thinking about the endogeneity of the network. You mentioned the dormitory one. So I think even if the roommates are exogenous sign of how you interact with your roommates is kind of endogenous. So in the sense, the network can be exogenous, but which one you choose, how frequent you.
Well, all right. So that's right. So you are told by the university who your roommate is, right? But whether or not you end up having an interaction with your roommate is entirely up to you, right? And any of us who've lived in, who here has lived in a dormitory somewhere? Only a few of you have lived like in buildings like this. If you have, you probably know that that there are many people who they take one look at their roommate and say, "I'm not speaking to you for the year," right? So that's not so when we can actually go out and survey people and say, "Who do you talk to?" then we learn something, right? But there are figuring out knowing what the network is when we have data which is one step removed, right? Is I think a bigger problem, right? For exactly the reasons that you say. We can't actually see the mechanism at work, and if we can't see the mechanism at work, we can only infer its existence. And what the guys who did the Harvard study did was actually to infer the existence of a network link from saying that that two people are roommates. But in fact, all that does is just increase the probability of a link. Doesn't mean that there actually is one. This is a real problem. There's an interesting paper concerned with the consequences of exactly that was published in Econometrica some years ago, not too many years ago, by Scott Carroll and West. I don't remember, there's a third co-author on this, having to do with manipulation of groups at the United States Air Force Academy, and an experiment which failed, actually, to try and increase academic performance by manipulating groups. And it failed exactly because there was this within group, you may be in my group, but, thing going on. So it's worth tracking that down. I think I've given you enough information. I only have 10 minutes. So I'm really going to move because I'm not anywhere near where I want to be. All right. All right. So now what I'm going to do is I'm going to start talking about some basics of network science. If we're going to talk about the effects of social networks, we need to be able to describe social networks, okay? So how are we going to do that? So what is a network? We're going to describe these things by graphs. And by graphs, I don't mean the functions that you learn to draw, like in 4th grade or something like that. You make these nice little plots like that. A graph is a mathematical object. It's like that picture that we saw of the village network, right? We have a bunch of vertices, V here, standing for people, and E, edges of the graph, okay? And we're going to talk about, largely talk about today about undirected graphs, which is to say where influence runs both ways, okay? Now, the graph that we talked about in the Glaser, Sacerdote, and Checkman paper was in fact a directed graph, all right? Because I was only influenced by the person on my left, okay? And I didn't influence him because if he's on my left, I'm on his right. Okay, that would be an example of a directed graph, and we can talk about those. Another thing we can do is we can put weights to say that maybe you influence me a great deal and you not so much, okay? And we can have weights on these things, and they need not be symmetric, too. Okay, but we're going to stick with this for simplicity. One thing we will want to talk about is, well, who are you connected to? So the degree of a node or a vertex, node, vertex, same word, or describing the same thing, one of the little dots, all right? The degree of a node in an undirected graph is the number of people that the person is connected to, all right? And we have to refine these things. We have to refine everything if we're talking about a directed network. Then we would talk about in degree, how many people influence you, and out degree, how many people do you influence. These would be 2 numbers rather than 1. We're not going to worry about that. We talk about a path in a graph. You'll remember when I talked about going from this guy to this guy to this guy to this guy down here. That is a path, okay? Traversing the edges. A geodesic is the shortest length path connecting 2 vertices. One thing that we will want to ask is how big, what is the span of a graph? And one measure of the span of the graph is to say, what is the largest distance, or what is the largest geodesic between any 2 people? If I measure the distance of 2 people as the length of the shortest path between them, I can ask the question, well, what is the size of, one way of talking about the size of the graph is to say, well, what is the maximal distance between 2 people chosen in the graph, okay? Or I could talk about something like, what is the average distance between 2 people chosen in the graph? A subset of vertices is connected if there's a path between any 2 of them. A component of a graph is a collection of vertices, which is, A, it's connected, and B, there are no left out vertices which also are connected to them. So it's maximal with respect to this property of connectedness. So you might imagine that I have a group of people over here that all talk to each other and another group of people over here that all talk to each other. And then there's no links between them, okay? And then I have 2 components, okay? Graphs have by the way, another useful word, a clique is a component for which all possible edges are in the graph. So when we talked about the village as a learning unit model, right, that presumes that a village is a clique. that everybody talks to everybody else. Okay? All right. We can represent a graph by a matrix. There are several different matrix representations of a graph. One that the only one we're going to talk about today is something called an adjacency matrix. So we're going to imagine a graph where each column, the ith column, refers to person I, and the ith row, I did that the wrong way. So here we have our matrix. Okay, we're going to take the ith row, that refers to person I. We'll take the jth column, that refers to person J. And if there is a 1 in the ij entry in the matrix, it means that person I is linked to person J. Okay? All right? Typically, by the way, we will not assume that people are linked to themselves. Our graph's 5 minutes, and our graphs don't have loops. Okay? If we're talking about undirected graphs, if I'm connected to you, you're connected to me, and so therefore this graph is symmetric. Okay? But on the other hand, if we're talking about directed graphs, right, I might influence you, but you don't influence me, so the graph is now asymmetric. And of course, if we want to study weighted graphs, we can replace these zeros and ones by appropriate weights. Okay, so here's an example of a graph just to tie these things down. Here's a graph that has 3 components, right? Here's a component, here's a component, here's a component. The minimum degree of any element in the graph is 1. A and B each have only one, are each degree 1 element, so C, D, and E. The maximum degree is 4. Let me see if I can find the degree 4 guy. That's H, 1, 2, 3, 4. The diameter of the large component here is 3, because if you look at this carefully, you can see that you can go from any person here to any person here in at most, walking across at most 3 edges. Okay? And another thing that's interesting to talk about, that people do talk about, is the degree distribution. Okay? Namely, what percentage of the people are degree 1, what percentage are degree 2, what percentage are degree 3, so on and so forth. Okay? And enough of that slide. Okay? So here are a bunch of things that I have, that people like to measure. Graph diameter I've measured, mean geodesic length I've measured, degree distribution I've talked about, component size distribution, right? We can talk about, well, do you have a lot of small components, or do you have, a few, do you have a few big ones and many smalls, or what? Okay, so we can talk about this is a meaningful thing to talk about. The clustering coefficient is very interesting. There is a saying that say that friends of friends tend to be friends. Okay? That says that if you and I are friends and you and he are friends, then he and I are more likely than not to be friends. What does that say? If you and I are friends and you and he are friends, and that means that he and I are friends, it means that friendship is a transitive relationship, right? Okay. In fact, one way of representing binary relationships is by drawing graphs. All right. Directed graphs. So one of the things that we will want to measure is if we have 3 people and there's a link from A to B and there's a link from B to C, so we have a bunch of people that, where we've got these 3 chains, right? Well, I'll call them 3 chains, 3 people connected up. The next question we want to ask is, well, what fraction of those are actually triangles, which is to say, that if A and B are friends and B and C are friends, then A and C are friends. What fraction of them are transitively closed, right? That's an important social measure that sociologists have written a lot about, and this leads to something, and the measure is something called the clustering coefficient. You're going to stop me, but let me talk about one social network before we stop. This is a social network that was studied, and it comes from a high school, an American high school, secondary level school, right before university. And this graph represents who is partnered with whom, okay? So blues are guys and pinks are girls, okay? And this is who are you having Yes. Okay. And what do we learn? I'm actually not sure whether it's intimate well, I'm not sure how intimate the relationships are, but these are at a minimum dating relationships, right? And perhaps more, we don't know. What's interesting is that I think somewhere in this graph there is only one same-sex relationship. I don't remember where it is here. What's really interesting in this graph is that we see there, and this was done over this was studied over a 6-month period. We see that there are 63 couples that are stable over 6 months. Okay, that's fine. On the other hand, we have this big component. So this graph has 63 components of stable couples, 12 like that, 9 like this. Okay, so on and so forth. And so we have a somewhat large number of rather small components, and then we have something that is called the giant connected component. And this is everybody's messing with everybody else, okay? Now you'll notice here that this thing looks a lot like a tree, right? It's not a tree, of course, because it loops around, but it looks a lot like a tree. And you'll notice that there are a few people here that we might really call social entrepreneurs, right? Who are really, having a lot of social interaction. Okay, so this structure of having a giant connected component, and that really is the technical name, giant connected component, right? Having a giant connected component and then lots of small components. This is typical of lots and lots and lots of social networks. Okay, and there are a number of interesting things to talk about. You can really amuse yourself. You can write whole novels about looking at certain sections of this graph and saying what's going on there. All right? But we're not going to do that. Instead, what we're going to do is stop and take a break now. Okay? So the last social network that I showed you, the high school engagement graph, if you will, comes from 2004. Here is a slightly older graph that comes from 2001. So this is the first thing came from a paper by Peter Behrman, who's a sociologist at Columbia University, and a fellow named James Moody, who I believe is at Ohio State, or at least was. And this is another Moody paper, Moody et al. And this again is a graph of a social network. Now you might say, what can you learn from a picture that looks like this, right? And the point of this graph was to illustrate a phenomenon which is very important in social networks, which is known as homophily. And homophily is the idea that like tends to be connected to like, okay? The way to understand this graph is that this is a picture of a social network of 7th and 8th graders at some school. So these would be kids, I guess, around, what, 12 and 13, I think, years old. And younger ones, the nodes are organized the following way. Younger ones are on the bottom, and older ones are on the top, okay? The nodes are also organized a different way. The different colors indicate different ethnicities, okay? And I believe the ethnicities are white, black, and probably white, black, and either Hispanic or Asian. I don't know which. I'm going to guess Hispanic, actually. And the other thing that we notice is, so what do we notice from this? First off, we have kind of a less dense area here of links going down, right, from older to younger, and similarly here from older to younger, okay? So there's not a lot of connection across grades relative to the amount of connection within grades. The other thing we see is that there is clustering of whites, there is clustering of blacks, okay, and the other group, as I said, I think they're Hispanic, are kind of mixed in. This is from a so-called middle school in Ohio. And so this illustrates very nicely this property of homophily. Homophily, again, is the idea that like connects to like. If we want to look, if we want to study action on a graph, we have to worry about, sources of correlation. And so we need to worry a lot about the structure of the graph. If we think, for example, that people who are alike are going to have a lot of common shocks, some of which common covariates, some of which we see and some of which we don't see, okay? The covariants we don't see, the so-called unobserved shocks, right, or unobserved components, if they're going to be correlated, and that correlation is going to be something that we're going to have to untangle, and this is a problem for empirical research, okay? Which I won't talk about because that's what Chris Tabor does. Yes?
Okay, what's the meaning each, the division of each dot? Does that mean their location in the real life?
No, well, all right, so this is not location in real life because this is a network of friends, okay? This graph was drawn in such a way that people were asked, who are your friends, right? And so there's an arrow from here to here saying that this guy said that this guy was his friend, okay? And sometimes the arrows go both ways, sometimes the arrows go only one way, okay? And this is common in these networks. Now, if you have this whole bunch of lines and arrows, you can lay them out in any way you want, right? They were laid out here in order to display a particular structure, right? So they used an algorithm for plotting these things that said, try and put the green things together as much as possible. Well, I guess what they did, actually, that's not what they did. What they did was they simply said, what the algorithms, here's how the algorithms for these things work. What you do is you imagine that on any edge is actually a spring, okay? And then you want to spread them out so as to see things, but you want to minimize the energy that you're using to spread everything out, because the springs are going to pull everything back together. And this is exactly, the way that one does graph visualization, and that's what was done here. So the fact that this is over here and this is over here doesn't mean that they're far apart in terms of distance in some sense. What it means is that these people here are mostly connected to these people, and that these people over here are mostly connected to these people, and there's few lines running across this way, and there's few lines running up and down that way, okay? So it's just meant to give you kind of the feeling, the shape. And this is a real big problem, right? Because this is a very high-dimensional object, right? And some people are really good at looking at 5-dimensional tables and figuring out what they say, but not very many of us are, right? So there is actually, a big business in graph visualization, for exactly this reason, okay? I'm going to skip this slide, I think. I'm going to talk now about models of graph formation, okay? I'm going to talk about this very briefly. There are two ways in which we model graph formation. One way is by thinking about strategic graph formation. We're all economists. We all understand that we are self-interested, and if I'm your friend, there must be a reason why, right? And so we can think about constructing a graph as the outcome, or a friendship network is the outcome of some kind of underlying game, right? And if we there's a large literature that does this. How many of you are familiar with the so-called Gale-Shapley marriage paper? A few of you are, okay? So this is an example of a graph formation model, okay? This, by the way, this is the paper. What is it called? On College Admissions and the Stability of Marriage. It is by David Gale and Lloyd Shapley. It is the reason why Lloyd Shapley won a Nobel Prize. It is published in a journal called the American Mathematical Monthly, which is a periodical which is published basically for high school teachers. Okay, it's a very elementary idea and a very important paper, and it raises the following graph formation problem. We're going to imagine that we have a bunch of men. We're going to imagine that we have a bunch of women, and the men have preferences over the women, and the women have preferences over the men. Okay, and what we want to do is we want to pair them off. Okay, this is marriage, in such a way that there is no man and woman pair not married to each other who would like to divorce their partners so that they could marry each other. Okay? So once we have everybody paired off appropriately, if I want to marry you, you prefer your partner to me. Okay? And such a graph they called stable. Okay? And then they talked about the existence of stable graphs and how to compute them. Okay? And how to find them for any preference order. Okay, and so this is a very important paper in its own right. It is kind of one of the foundational papers for the so-called market design literature, and this idea has been generalized by Matt Jackson and Asher Walensky in a paper where they said we can apply this general stability idea to arbitrary graphs, and we will call, for example, a graph stable if nobody, I'm going to take a graph and we're going to call it stable, if there is no link that any one individual is a part of that he or she wants to drop, would be better off dropping, assuming that nothing else in the graph changes, okay? And there is no link which is missing that both people would prefer to have, okay? And this concept is called pairwise stability. All right, and it is an obvious generalization or an obvious stretch of the Gale-Shapley model, and this has been being used. It's kind of a hot topic or a mini hot topic in econometrics now to think about estimating models where graphs are formed according to the stability criterion. Now this sounds a lot like Nash equilibrium, but it's really not Nash equilibrium. Because if you really thought about Nash equilibrium, how does a game work? You have a bunch of strategies, right? And then you have a payoff function on all the strategies here. Well, what is a strategy for the marriage game, right? It's hard actually to know how you would write down the game. What are the rules for finding a mate, right? You can't really imagine how to do this. So my understanding of stability, so if you read the Gale-Shapley paper, they will talk about how this is a generalization of the idea. They're kind of coming out of cooperative game theory, something probably none of you have studied or you've only studied a little bit. You might have heard of the core, for instance, which is a cooperative game theory concept. So this is, stability is kind of Gale and Shapley thought about it as a cooperative model. I think about it as a non-cooperative model. I think of the idea is that I don't really know what the rules of the game are for marriages or for social interactions of different kinds. I don't know what they are. I cannot, and I would also imagine that if I wanted to get really sharp predictions, okay, that the very fine details of the rules would matter so that getting it wrong would be a really bad thing, okay? So I think of stability as kind of a cheat. What stability says is that, well, you know, if we have, at the end of the day, if our rules are sensible, right? People are not going to get stuck with relationships that they don't want, okay? If there's any kind of strategic component involved, they're not going to be stuck with relationships they don't want, and maybe more questionably, they're not going to miss opportunities, okay? And I say that the latter thing is in some sense more questionable because in a large population, there might be opportunities, but you would have to find them, right? But this then creates a lot of this itself suggests that there's theorizing to do. You could build search costs into this kind of thinking if you wanted or something like that. But this whole approach, right, is the strategic approach. And I think it is, it's popular. It is also limited for ways that I'm not going to talk about now. But if you'd like to know more about it, you can talk to me afterwards. There's also a literature having to do with the statistical analysis of graphs. If we talk about the statistical analysis of anything, think about a data set. When we want to talk about the statistical analysis of the data set, how do we do that? We begin with a probability model, right, which describes the data generating process, right? Isn't that what we do? And then we use this probability model to engage in inference. Okay, we construct estimators, functions of the data, we estimate, we compute the mean and the variance of the estimators and so on and so forth, right? All of this comes out of this data generating process, this probability distribution that we've assumed at the outset. Does everybody understand that as a description of econometrics? I'm really glad that our econometricians are not here. But I think that's right. That's what we do. Well, same thing with graphs, okay? If we want to talk about graphs, what we can do is we can describe a data generating process, a statistical model of graph formation, a probability distribution on graphs, okay, and then use that to do inference, okay? And so I'm going to give you a quick introduction to one of these models. It's not particularly good for social networks, but it's one model that we can all understand, okay? Here's the model. We have a bunch of individuals, okay? We draw two individuals. We take two individuals. We do this for every pair of individuals. We flip a coin. If it comes up one way, we'll say we're linked. If it comes up the other way, you're not linked. All right? So the existence of, so we can write down the set of all possible links, and then we can realize them through the flip of a coin. This is called the Bernoulli random graph. It's sometimes called an Erdős-Rényi random graph. These are two Hungarian mathematicians, okay? If any of you have ever heard of Erdős numbers, that's Erdős, okay? So every possible edge, every VW pair is actually assigned as an edge. It's put into the list of edges with probability P. Now, an interesting exercise, and one that we often do when we analyze graphs. Remember, what do we do when we have a data set, right? The first thing we do is we say, well, we want to think about, for example, consistency of estimators, right? So what do? We assume, let's let the data set get very large. Let's let n go to infinity and see what happens. And then we compute limit distributions and stuff like that, right? All right, so we can do the same thing here, all right? What we're going to do is we're going to study sequences of graphs that are constructed with this way, such that, which have the property that the expected degree for any node, okay, is fixed, okay? So suppose that we have a graph with n people. Then there's n minus 1 individuals that I could be paired with, okay? And the probability of realizing each one of those pairs is in fact p. So the expected number of pairs that I have is p times n minus 1, all right? So what I'm going to do is I'm going to let n get very large. If I just let n get very large alone, I'm going to end up having an infinite number of friends. Sounds kind of ugly, right? So what we're going to do is we're going to let n get very large. We're going to let p get very small in such a way that the mean converges to a limit, z, okay? So we're making ever larger and larger graphs with the same expected degree. And now we want to know, well, what does this graph look, and so the limit thing, we can think of this, what does this remind any of you of? This exercise of doing something with binomial distributions and letting n get large and p get small. This is a test question. Think from probability theory, where have you seen this? You want a hint? Think French word for fish. Yes? Louder? Poisson distribution, thank you. That's right, that's what it is, right? Isn't that how you derive the Poisson distribution? How many of you have ever studied this? How many of you know what the Poisson distribution is? I'm in China and only a few hands are going up, and you're all graduate students? Really? Ooh, okay, gosh. Okay, well, the rest of you, get your stat books out. Go look this up. The Poisson distribution is a very important distribution, and this is kind of a graph theoretic version of the Poisson distribution. The Poisson distribution is exactly this thing where we do, we have a larger and larger number of samples, an ever larger sample size, but we keep the success rate the same, okay? or we keep the expected number of successes the same, and then we want to ask things like what is the variance and so on and so forth. And the Poisson distribution has lots of uses, okay, which we're not going to explore here. So we want to study these so-called, so these things, these limit objects are called Poisson random graphs for obvious reasons, right? We're essentially replicating the idea of the Poisson distribution. The key parameter is z. Z is the expected degree of any individual in the graph, expected number of links. Now, what we see is the following. When z is small, when z is less than 1, we expect to see, and we can, this is all provable, okay? Rick Durrett, you can write down that name if you're interested in the mathematics, has a book on random graph theory, D-U-R-R-E-T-T. And he proves this carefully in the book, that what you will expect to see is a large number of small components, okay? So the graph will essentially be many, many, many islands. The size distribution of the islands will be an exponential distribution whose parameter depends upon z, okay? All right? That's simple. Now, when z moves above 1, we get a very, very different picture. And the picture we get will remind you of our sexual graph from our high school before. We get what is called a giant connected component. What do I mean by a giant connected component? There will be one component. So one of the things I guess I should say is that when z is less than 1, and we have these components, the mean component size grows like the log of n. All right, so it's kind of, like this. You know what log looks like, right? Okay. So when z is greater than 1, if we look at the largest component, the size of the largest component is growing linearly in n. All right? And that's going to be a giant component. And the giant component is unique, typically, okay, with probability converging to 1 as n gets large, okay? And all of the rest of the nodes will be these small little islands, again, distributed exponentially in size, okay? All right? So we'll have this giant component, like we did previously, and then we'll have all these little small things, all right? And what fraction of the population is in the giant connected component, right? Well, when z is very, very near 1, okay, it'll turn out that that fraction is going to be very small. That fraction is growing linearly in n, but it might be like only 1/10 of 1% or something like that. But it's still growing linearly in n, where everything else is growing log-like, okay? We're just getting more and more and more islands as n gets big, okay? The giant connected component is getting bigger linearly, all right? Then when as n moves away, as z moves up and gets bigger and bigger and bigger, what's happening is that the fraction of the population in the giant connected component is growing and growing and growing until it gets very close to 1. Okay? This phenomena, where if we look at the size of the largest component, it's essentially very small. This is from a simulation. Very small, suddenly we cross 1 and it takes off. This is called the phase transition. Okay? Much has been written about phase transitions. So, for example, I have a paper that talked about graph formation and talked about a version of stable, okay, when we had random graphs. It had a version of stability. Here is the problem. We might imagine something like this paper started out as a model of financial market collapse, but it turned out to be a model of AIDS or some disease, okay? Because it turns out that it's really hard to do finance in graphs very well. So the way the story goes like this is we can imagine that I get benefits from being connected to more and more and more people. And if I'm thinking about financial diversification, this is a good thing, right? But on the other hand, if a financial collapse comes, right, and firms start collapsing, okay, then I don't want to be, the more I am connected, the more I am at risk of losing my assets because I can't collect on a bunch of my loans, right? So, the problem here is that there are benefits to my immediate connections, but there are costs to being connected that come through the network, okay? And we envisioned, therefore, that one could imagine this process of transmission of a financial shock through the network as drawing a random subgraph from a pre-existing graph that we already formed, okay? And then we could compute the expected value of different graph structures, assuming that by essentially asking the question, what is the probability that I am in the subgraph that is connected by through a financial collapse? And so it is essentially a random graph inside a constructed non-random graph, and we were able to show, I'm sure much of this is opaque, but what we were able to show is the following, that of course if you keep the number of connections you make small, the probability that you're going to go bankrupt is negligible, okay? But if the probability just gets a little bit too big, suddenly you are exposed to a significant risk, okay? Nonetheless, it turns out that the optimal thing to do, you can actually compute the optimum graph, turns out that the optimum is for everybody to be exposed to a little bit of risk of collapse, okay? It is not optimal to have a graph where everybody is perfectly insulated because then you have too little risk sharing, okay? But on the other hand, what is stable turns out to have just a few more connections, okay? And that few more connections just destroys optimality. I mean, you are so far away from optimal, you couldn't be farther away in utility terms. This is very interesting. It says that exposure to systemic risk, some exposure to systemic risk is optimal, but we might expect to see in a financial system too much exposure to systemic risk, and the difference between optimal and way too much is very, very tiny, and therefore something that is going to be hard to control by regulation. And that financial story that I just told you, right, comes out of analyzing graphs that look like this, or that are graph analysis that is based on this kind of thing. This idea of the giant connected component is most easily seen in talking about Bernoulli random graphs, but it's really present in almost any random graph model you can think of, okay? So it's an important thing in one of those important facts one should know. All right, let's talk now about something else. Let's go back and talk about transitivity and homophily. The idea of transitivity is that if two people in a social network have a friend in common, then there's an increased likelihood that they will become friends themselves at some point in the future. This seems to be an accepted fact in sociology. I don't know how well established it is, but it is accepted, okay? If you go and look at my slides, and you look at one of the slides we skipped, you'll see the measure of the clustering coefficient for a number of different social networks that have been studied, and you'll see that these clustering coefficients are reasonably high, meaning that a number of these three people groups that are connected to each other are in fact closed, okay? It's a decent number. More than you might expect if you were just doing things entirely at random, okay? Why? So the question I want to look at my notes, say, what is it that I actually want to say about this? What I want to say about why do we see transitivity, okay, in social networks? Why do we see this kind of clustering of people who are similar? Well, why do we see, in general, large amounts of transitive closure? There are several reasons that I can think of. The kind of obvious thing is, first is constraints. The people that I'm going to meet in a social network of some kind, I mean, if I'm in a social network, I have pre-existing friends. Whom am I more likely to meet? I am more likely to meet friends of my friends than I am to meet random people, okay? Or at least have enough exposure to friends of my friends in order to establish my own links. Imagine that if you're walking around on the streets of Beijing and you run into somebody on the street that you don't know and you have a short conversation. I don't know if this could even happen, but suppose that it could. What is the likelihood that it would ever happen again, right? But if you've got a friend, and you go to a party with your friend and there's someone there that your friend knows that you don't, well, you're liable to go to other parties, right? with the same friend, and maybe the same person will be there. And that's a more likely event. You're more likely that that person will become a friend, right? So there's an issue of constraint, opportunity. The people that you are most likely to be able to establish links with are friends of your friends, because they're the people you're going to see them more often, okay? There are also some taste reasons as well. What are the taste reasons? Well, one is homophily, that our friends' friends tend to be, our friends are like us. Our friends' friends are going to tend to be more like us than is a randomly chosen person, and therefore we have more in common with which to build a friendship, right? Or more common need for a link if we're thinking about other things like firms and stuff like that. Sociologists have a third idea, which has to do with, I would put in the category of incentives. Sociologists will tell you that there is a latent stress in a social network where there's not a lot of transitive closure. And I don't really understand what latent stress is, having read many sociological descriptions of it, but it seems to me that it has something to do with incentives, right? That it makes my friends happy, for instance, if I become friends with their friends. It makes it easier to have social situations and stuff like this. I think this really, really depends upon the context in a way that the other two things don't, okay? But for example, for some of the networks that we've looked at, this kind of thing is very important, and we would expect to see, therefore, more transitive closure than otherwise. All right, another topic. One of the things that we want to talk about in a graph, we have a social network of some kind. Maybe it's a network where we're thinking, let's go back and think again about transmittal of knowledge about a new technology, picking up these pineapples, for instance, okay? Who's important? If we go back to that picture that we saw earlier, we should ask the question, who is important in the network, okay? Well, how can we formalize the notion of importance? What do we mean by importance? If we're thinking about social learning, we might want to say, well, you know, an important person is a person who has the most influence, a person whose information reaches the most people or has the biggest impact in some way, okay? So there's many different ways of measuring importance, because even what I just said sounds really vague, doesn't it? What does it mean to say that I have the most influence, or that I reach the most people, or I reach the most people that I can actually easily influence? I mean, if I can reach you, but 30 other people can reach you, I'm not terribly important to you. So maybe you shouldn't count so much in calculation of whether or not I'm important, okay? So this is a hard thing to sort out. Not surprisingly, there are a number of different importance measures, and I want to talk about them briefly. One is the notion, misspelled, of degree centrality, okay? We're going to be talking for a moment now about measures of centrality. Degree centrality says the centrality of a node, the importance of a node, is measured by the number of people that it connects to, okay? All right? So if I am that, if you remember our sexual network, you remember there are one man and one woman who seem to be connected to a lot of people of the other sex, right? Those are people whom, according to this measure of degree centrality, are going to be very important, okay? Why might you want to know that? Suppose your problem is you want to stop the transmission of sexually transmitted diseases in this school. And let's suppose that there's a lot, that this is in fact a sexual contact network, okay? Right, just to make it real, okay? Well, who, you know, and you have limited resources, or you want to find the most effective way, right, of stopping the network, right, of stopping the flow of these diseases. What do you want to do? You want to find the most central people, the people who are really kind of, you know, most active in some sense, or most important in spreading this thing, and those are the people that you want to give drugs to. Those are the people that you want to give contraceptives to. Those are the people that you might just want to kick them out of school. Who knows, right? Probably wouldn't work, but, you know, whatever, right? There's the policy question, all right? So, well, degree centrality is an obvious candidate, right? These people are immediately reaching out to a lot of other people. Maybe these are the people that we need to fix. There's another question, another notion of centrality, which is due to this fellow named Katz. It's called Katz centrality. How many nodes can individual I reach? Okay, So let's go back for a moment and think about our adjacency matrix. Our adjacency matrix, can I write on this board? No? Yes?
Yes.
Okay. I thought I heard someone said no, and I said, there's a whiteboard I can't write on? All right. So we're going to imagine that we have some kind of, well, maybe I can't write on it. Oops, and I didn't want to do that because I just made a mistake. And one more. Okay, so here is an adjacency matrix. All right, I'm going to label our people. So person number 1, I haven't made this symmetric, have I? And maybe I should make it symmetric so that we're consistent with the stories that we've been telling today. This needs to be a 1. If I'm going to make this symmetric, let's make this a 0. So that's a 0, that's fine. 1, 1, 1, 1, 1, 0, 1, that's fine. And we'll make this a 1. Okay, now we have a symmetric graph, right? Is it symmetric? Did I screw it up yet? Not yet. Okay, good. So here we have a symmetric graph. What does it mean? What does this say? Person 1 is connected to person 4. Person 2 is connected to 3 and 4. Person 3 is connected to person 2 and person 4. And person 4 is connected to 1, 2, and 3. Okay? Now, let's multiply this matrix by itself. Let's take a squared. Now we're going to compute this together. If we look at the 1, 1 element, it's going to be 0 times 0 plus 0 times 0 plus 0 times 0 plus 1 times 1, right? Okay. Let's look at the 1, 2 element. 0 times 0, 0 times 0, 0 times 1, 1 times 1, right? So we also get 1, right? What about the 1, 3? 0, 0, 0, 1. And what about 1, 4? 0, 0, 0, 0, right? Okay. So let's just look at this row, because I don't want to do the whole thing. Main reason is that I'll get it wrong at some point. I'm not very good at arithmetic. I'm much happier in higher dimensional spaces. All right, so what are we measuring here? Well, let's think about the multiplication formula. The multiplication formula to get the number, the ijth element of a squared is ai1 times a1j, right? So that is going to be either a 0 or a 1. It's going to be a 1 only if ai1, right, is a 1 and a1j is a 1. If both of those things are a 1, what does it say about the graph? It says that there's a path from I to 1 to j, okay? So it says that there is a length to path between I and j, okay? Now, so again, ai2, a2j, ... We sum all those up. What are we counting? We are counting the number of length to paths between I and j, okay? So that's what a squared is telling us. It's telling us the ijth element of a squared is telling us the number of length to paths from I to j, okay? ai can be equal to a positive number now because there can be a path from, in fact, typically in an undirected graph, it will be a positive number because there's a path from me to you and that path comes back to me at the second step, right? Okay. What do you think happens if we look at a cubed? What are we counting there? This is a test to see who's still awake. If A counts the number of length 1 paths between any two people, which can be either 1 or 0, right? And a squared counts the number of length 2 paths, what do you think a cubed is counting? Out with it. Paths of length 3, right? right? And AN is counting the number of paths of length n. See, this is the social norm. You're all saying, no one asks us questions. Professors don't ask us questions. Well, this professor does. And wait, you know, I'm going to be the easy guy. Wait until later in the week. You know, you get that Chow Fu. She's going to be beating on you guys if you don't answer her questions. And we have seen this, haven't we? You know what she's like. She gets furious, right? So start practicing, okay? All right, so that's what. So what are we measuring here? We're looking at the ijth element of the matrix AK. So this is the number of paths of length k between I and j. And now what we're going to do is we're going to sum them up, okay? But we're going to say that longer paths are less likely to be influential than shorter paths. And so we're going to discount them by the length of, according to the length of the path. So we're going to choose a discount factor alpha, which is between 0 and 1. And then we're going to take this discounted sum, okay, going out to infinity, okay? And therefore, what we're looking at basically is what are the number of distinct paths, when we look at this number, forgetting this, we're saying we're looking at the number of distinct paths of length k from I to somebody, okay? And then we're discounting that total number of paths by a raised to the power of the path, and then we're summing it up. So this is a measure of influence. It is a measure of how many people, different people at different lengths you're able to reach, okay? And in thinking about what is the right alpha, well, this depends upon what we want to do. Now, I'm not going to derive it here, but if we took the time to do it, you can see, for example, that as alpha goes one way, which way does it have to go? As alpha goes to 0, and if we normalize this the right way, okay, which we have to divide it by 1 minus, we have to multiply it or divide it? We want to multiply, I don't remember. There's a way of normalizing this, and I don't want to think it through right now. We would get, as alpha goes either to 0 or to infinity, but I think it's to 0. We would see that we're going to be measuring degree centrality. If we go the other way, we're going to be measuring something else. But the point is that this is a measure of centrality that says we don't just care about who you're immediately connected to, but you're connected to who you're connected to farther out. So for example, if we had some person in that sexual graph who was connected to all these people, but none of these people were connected to anybody else, okay, then this person really might not be so important, okay? Whereas we might have another person who is basically has only a few partners, but is the root of a tree. And they might have a lot of influence then, right? And of course, whether or not that's important is going to depend upon what alpha is, whether alpha is nearer 1 or nearer 0. All right? All right. Eigenvector centrality. This is really important. Okay. When am I influential? I am influential if I influence influential people. All right? Everybody got that? If you're not influential and I influence you, okay? But this guy here, he influences the world. So when I influence you, wow, that makes me an important guy, okay? So how might we do this, okay? Imagine the following. Suppose that I could give a score, an influence score, to everyone in the room, right? And then what I could do is to measure my influence, okay, by summing up the influences of everybody that I influence, okay? And we can do that for everybody, all right? So, I guess a better way to say this is what we're really going to be doing is we're going to be measuring proportional influence, all right? So I am proportionately more influential than you are if I am influencing more influential people. How am I going to measure this? Suppose I have a score of influences X, okay? And if I had my matrix A, okay? Then if I, here, so remember, we're going to take, say, suppose I'm person 1. If we multiply x by a, we're going to get a row, x is a row vector. We're going to get a new row vector out. What is the first component going to be? It's going to be x1 times a11 plus x2 times a12. I'm sorry, a21 plus x3 times a31, right? Okay. So those a's are going to be 1 or 0 depending upon whether or not I influence them, okay? And so what I'm doing is that when I do that multiplication is I'm just summing the influences of the people, right, that I influence, okay? So what am I going to get? I'm going to get out some number, and I'm going to say that my influence score has to, so we're going to get out some number y, right? We're going to get out a vector, we're going to get a y1 for me, a y2 for you, so on and so forth. But the point is that when we do this the right way, we want to get back the numbers that we started with, or at least numbers that are proportional to the numbers that we started with. Remember, we're measuring relative influence. What is my influence relative to yours? Okay? All right. So that suggests that we want to measure influence by looking at a solution to an equation system of the form like this, where mu is a constant. Okay? So this says if we start with a vector of influences where xi over xj measures i's influence relative to j's, okay, and then we compute this product, we're going to get out a vector y, right, where the proportionalities are the same, right? So if we call this to equal y, then we see that xi divided by xj is going to equal yi divided by yj. The constants, the proportions are fixed. Okay? Do you get the idea? Okay. What do we call this object? What does that remind you of in linear algebra? Louder? Right? Mu is an eigenvalue, right? And x, right, is an eigenvector. Okay? Now, here's a little hint. Suppose that A has the property that everybody is connected to everybody else, indirectly. Okay? The matrix will have the property which is known in matrix language as irreducibility. Okay? So this is a non-negative and irreducible matrix, right? And there is a theorem in linear algebra which is very easy to prove called the Perron-Frobenius theorem. Who's heard of the Perron-Frobenius theorem? Like anyone who's ever taken a macro class has heard of the Perron-Frobenius theorem. So basically, keep your hand down if you've never had macro, okay? You've all heard of it, right? So the Perron-Frobenius theorem says, right, that, well, the Perron theorem says that if you have a strictly positive matrix, right, it is going to have a single eigenvalue. Remember, eigenvalues can be complex numbers, right? But it's going to have a single eigenvalue which is largest in magnitude. Magnitude of complex numbers, we know how to compute, right? So it's going to be largest in magnitude. That eigenvalue is going to be real and positive, and the corresponding eigenspace is one-dimensional, okay? Frobenius comes along a little while later and says, well, if you make the matrix non-negative and irreducible, the same conclusions hold, okay? And that's the Perron-Frobenius theorem. So if we look for we are guaranteed, oh, by the way, another thing that the theorem says is that this vector x, right, is going to be a semi-positive vector. In fact, it's going to be a strictly positive vector, right? And it is the only strictly positive eigenvector. It's the only strictly positive eigenvector. So what that says is that if we look for a non-negative solution to this system, it says that it's with some mu, there's a unique solution if A is irreducible, which is to say that if the matrix is connected. If the matrix is not connected, you can do this component by component, but then you can't say anything about the relative importance of a person in component 1 relative to another person in component in person 2. Okay? Another person in component 2, jet lag again. Okay? This idea was introduced by a guy named Phil Bonasich back in the 1980s, and it has a lot of application. For example, how does Google do searches? Right? What Google wants to do is find important websites, right? So the original PageRank algorithm essentially took the web, right, and it looked at what web pages linked to other web pages, okay? And it says, well, if we want to measure importance, okay, what we should do is compute the eigenvector centrality, okay? And that's essentially what it did, okay? And then it was refined because what's important to you is different than what's important to me, and so Google has all kinds of stuff going on there, some of which we know, much of which we don't, right? And it doesn't matter if you're here, because what Google does is irrelevant, right? Okay, but DuckDuckGo, or what else do you guys use?
Baidu.
Pardon?
Baidu.
Baidu, okay. Baidu, I haven't tried because it probably won't help me, right? But Baidu, same thing, right? This is the fundamental idea. So much for eigenvector centrality. Here we are again talking about homophily, which has come up a lot. This is a map, as Valerie immediately recognizes this map, right? This is home down here, University of Chicago right down here. This is a map of the city of Chicago. I use this map a lot. I love this map, okay? The guy who wrote this map, who drew this map, said every one of these dots represents 20 households, right? And the color of the dot represents the average ethnicity of the group, okay, of 20. And Chicago is laid out, there's a lake here. This is called Lake Michigan. It is a beautiful lake. There's a nice little trail. You can ride your bike all the way here until you get to Gary, Indiana, at which point you fall off your bike. And here is downtown Chicago. Here is the University of Chicago. Here's Northwestern University, okay? And here is O'Hare, the big airport. That's all the important. Where's Midway? Midway's here somewhere. I guess down here somewhere. That's all that's important in Chicago. That's not true. All right. If we look at this map, what we see in this map, these are physical locations of households, and these locations are colored by the average. By essentially the ethnicities are scored according to some number, and then these are colored according to the average. And I think it's 20, it's either 10 or 20, I don't remember which, in the sample, okay? So we look at the 20 houses around you, and we do this all the way through. And you'll notice in this picture, this is called the dot map. And it's a very interesting way of displaying variation. The gray stuff is basically non-residential, right? This is a highway here, for instance. I guess this must be a highway too. So pink are, these are white households. Blue are black households. Orange are Hispanic households, and there's a little bit of green, and those are Asian households, okay? And this is the picture. And what we're supposed to notice in this picture is that there is a great deal of very sharp boundaries, right? You can see here, even here where, it's kind of mixed, it's not really very mixed. Up here, it's a little bit mixed. It's not very mixed, okay? You don't see kind of areas where there's lots of blue and purple or blue and pink kind of interspersed here. People of similar ethnicities strongly tend to live together in Chicago, okay? I don't have a picture with me here. I should actually put one in the set. But somebody did the same thing for stratifying households by income, okay? You've, I think, seen this because I've shown this before. And the boundaries are much more diffuse. You have a lot of poor people living very, very near rich people in Chicago, okay? Which might be a surprise to people living in Chicago, but this turns out to be true, okay? But ethnically, we see that there is a great deal of sorting going on here, okay? And in the meantime, if You've all been reading this quote. I only know about this because this is what Stephen Durloff does. He comes up with these really massive quotations from Greek guys, and he's included this in a paper we once wrote together, and so I decided it would be a nice way to fill out the rest of the slide. This slide illustrates this important phenomenon of people sorting each other according to similarity by type. Why do we have homophily? We have status homophily. We feel more comfortable when we interact with each other, with those who have a similar cultural background. We have value homophily. You'll find this in the sociology literature. We often feel justified in our opinions, or for that matter, in our behaviors, when we are surrounded by others who share the same beliefs, or I should also add the same behaviors. And then we have opportunity homophily, that we mostly meet people who are like us. Homophily, in fact, poses a problem when we want to estimate effects. Right? Here is a graph, and this graph comes from a very well-known study in the social network literature having to do with obesity. Okay? This data comes from a very long-running panel data set of people with live in an area not too far from Boston called Framingham, right? Which some of us know is the home of Friendly's ice cream. Did you know that? Probably. And this is a panel data set that now is multi-generational. Let's see, as I recall, I actually need to look at my notes for this. This work was done by a guy named Nick Christakis and I don't remember, and Jim Fowler. Purple lines represent genetic links between people, namely, parents or, or I guess cousins. I'm not sure. Size is proportional to the body mass index. If you have a high body mass index, you tend to be large for your size. So here, for example, is a really big person, okay? And on the other hand, this person here, really thin, okay, relative to their size. That's what body mass index measures. People whose nodes are yellow actually fall into the official medical definition of what it means to be obese, which is to say excessively fat. Red-rimmed, if you can see this farther back in the room, red-rimmed people, like this one here, red rims are female, non-rimmed are male, okay? So this is a picture of a social network that encodes a lot of different information about people. And what we are supposed to notice here is that there is a lot of clustering by obesity, okay? Christakis and Fowler studied this network using a number of different statistical tools, and they came to the very controversial but highly publishable conclusion that fat is contagious, right? That if you have obese friends, you are likely to become obese. Okay? You can imagine what happened when this hit Nature, right? Or they publish in Nature or Science, I don't know, right? One of the soundbite science magazines. And this is very controversial. The statistics here, I think, is actually quite bad. Stephen has a student whose name is Ethan Cohen Cole. Ethan and another student and another co-author of his published a paper in 2008 which essentially took this paper apart. The references are in the notes, and so you might, I think that the statistical issues here are very complicated, and if you want to think about doing work on social networks, there's no better place to start, well, maybe not start, but maybe be your third paper or something to read, to take something that's very controversial with an important result, where the statistics are complicated, and to see how things can go wrong, okay? You learn by mistakes more than you learn by the right stuff, I think. What are the problems that you can come across in doing this? Well, if we suppose that the attributes are fixed, okay? I mean, suppose it just happens that obesity is entirely genetically determined. Probably not the case, but suppose that were true. Well, then what we would find in the social network is we would just see homophily, right? We would see that people who are obese tend to have obese friends. That's a selection issue, right? But it's not evidence of any kind of causal claim at all, okay? If our theory is that if this graph is consistent, okay, with the idea that people who are fat have fat friends, it could be because they seek each other out. On the other hand, if the attributes are, if the attribute is variable, right? Maybe in other words, obesity is something that comes upon you, right? Or is a result of choices that you make. Okay, to the extent that that's true, then this would be a measure of social influence. Okay. Now the problem is, how do you untangle these two things? Okay. All right. How do you decide which way it goes? Does the causal arrow point this way or does it point this way? Right? All right. So, we've all heard the phrase that correlation is not causation, and this is the network version of it. Okay. And untangling these causal arrows when we think that networks are endogenous is a kind of the major issue that people complain about when they see empirical work on networks today. So if you were to write a paper using social networks to talk about things like educational outcomes, and you gave it at a conference somewhere, the first thing that would happen is someone would raise their hand and say, well, what about endogeneity of the network? Okay. I mean, it's like you press a button. Okay. And this is something I think that we get a little bit crazy about. This is an example of why we should be somewhat crazy about it, okay? But one way of thinking about it is the following. There's a lot of behavior that actually happens rather quickly. Do you commit a crime? Do you not? Okay? There's other behavior that happens rather slowly. How well do you do over the school year? Or do you really become obese because of your choices, smoking and eating the wrong foods and stuff like that, okay? Networks, friendship networks, take a certain amount of time to form. Maybe contractual networks in firms, for example, might be, much more quickly to form, much more quickly to dissolve, okay? Once you've got a friend, you might be stuck with the influence of this person for a very long time, whether you want it or not, right? So networks have duration. Behavior has duration, right? Comparing these two things is going to tell us whether endogeneity is really going to be important, okay? It is not the case that we will ever see a social network that is immutable, that is fixed, okay, for all time, which is what true exogeneity would really require. So we have to use our judgment in thinking about, do I really want to worry about selection here? Right? Is the behavior that I'm looking at transient relative to the duration of the network that I think is driving things? And that's kind of a judgment call. There's not been a lot of econometric work which has actually thought through the effects or the biases that come about when, say, duration is long but not infinite. Okay? If anyone here were inclined to econometric theory, I think that there would be kind of a quick and maybe neat paper to actually write on that topic. Okay, I actually even have a come and talk to me. It's a nice idea. Okay, how do we measure homophily? The obvious way to measure homophily, it's on this picture. You can look at it. I have 10 minutes. You can see if there's. I didn't even get to the model that I really want to talk about. I'm going to talk about it. Just compare how much cross-group matches you have relative to relative to what you would have with random matching. Okay, random matching, it's easy to compute what the fraction should be. Where do we see evidence for homophily? If we see more intergroup matching than we would expect, and there are obvious ways of measuring this. Okay. I don't want to talk about this. I want to talk a little bit about inequality in labor markets. I feel in the 10 minutes, which might turn out to be 15, that I want to actually say something about an economic problem, which many of you are going to be interested in, which Xiao Fu is going to be talking about when she gets here, okay? And this is the effect of networks on inequality in labor markets. So there's a lot of evidence. Here's a graph of wages from the United States. We know that there are there's evidence of persistent inequality in labor markets. There's a bunch of data here that I'm going to skip. I am not the guy to talk about data. One way to think about inequality in the effects of networks on inequality in labor markets is to ask, what are the effects of networks? How do networks impact how people get jobs, right? Right at the outset, you come to work, you graduate from school, you're ready to go to work, right? Your networks have an impact on the kinds of jobs that you have access to. Or maybe they don't, right? What is the evidence for that? Well, here is a table that has data from a number of different studies, 1951, 1970, 1974, 1980. These are different data sets constructed at different times in American history. This is all American data. We have different kinds of jobs, okay, that you can read here, okay? And this table, in this table, people ask the question, in all of these different studies, okay, how did you get your job? And what we notice in this table is that most people tend to get jobs through friends and relatives. You hear about a job through a friend. You get referred to a job through a friend or through a relative. A gate application. What do I mean by a gate application? There's a factory. You walk up to the factory, you fill out a form, and they call you if they want to hire you, right? That tends to be somewhat useful, not in Mary Corcoran's study, but where she didn't collect, but in all these other studies, that's somewhat useful. Employment agencies, not so much. Answering ads that are placed in the newspaper or online, something like that, not so much. Really this, okay? Now we can think, well, gee, what about all these online job sites and things like that, right, that we all know about, right? We have a number of these, like in the United States, Monster.com is one. I'm sure you have a number of these here. They tend to be very important, but in really very few, in a very small number of industries. So their overall impact on the labor market is rather small. Their overall impact on the number of people who write papers about them is kind of large, but so what, right? All right, so I want to tell you a story about weak ties and labor markets, okay? So Mark Granovetter is a sociologist at Stanford University, and he had the following idea, okay? His idea was that there are two kinds of ties. There are people who we are closely connected to, and now we might think again about the importance of homophily. These are people going to be family members. These are going to be friends that we share a lot of friends in common with. And then there are other people in the world that we have occasional contact with, okay? Maybe someone that we do sports with from time to time, or maybe just a friend of a friend and we bump into each other from time to time. What in English we would call acquaintances rather than friends, okay? And Granovetter calls these weak ties. And he writes here about different ways in which we might characterize strong and weak ties. But he says no matter how you want to characterize it, we all have an idea of what we mean by a strong tie, what we mean by a weak tie. The Americans in the room will recognize this the phrase when I call this an elephant definition. If you remember or not an elephant definition, what is it really? It's the pornographic definition. If you remember the Supreme Court definition of pornography, this is it. I can't define it, but I know it when I see it. Okay? Famous Supreme Court justice said this in the United States about pornography, and this is what Granovetter says about weak ties. I can't really give you a good definition, but I know it when I see it. We're going to just agree on some measure and move along. Why do weak ties matter? Okay, so here's kind of a story of weak ties. This is the story that Granovetter tells in his book, which is actually He wrote in 1973. It was his PhD thesis. And he's a very distinguished sociologist, but this might be actually his greatest work. We're going to imagine that we have two cliques. Remember what a clique is? A clique is a strongly connected, a group of nodes where everybody's connected to everybody else. Now what I'm going to do is I'm going to introduce a link between A and B. What is this? This is a bridge between A and B. This is a pretty powerful idea, this bridge, because now these two groups are connected and stuff can flow from here to here. Right? This might be my family group down here. This might be some other family group up here, and by virtue of some link here, okay, we're now connected in some way and information can flow. All right? So now I've added another link, and now we're going to say, well, there's not a single bridge anymore, but these things are local bridges. What do I mean by a local bridge? I mean a local bridge is a link between nodes in two different cliques, okay, such that each node has only, that each endpoint is the, so let me just say it this way. Let's look at A and B. A to B link is a local bridge because B is the only node here reached by A, and A is the only node down here reached by B, okay? So there's not a lot of nodes coming out like that. There's not a lot coming up like that. So it's still really performing this bridging function. And I should look at my notes. Wow, okay. Hang on one second. Okay. So now what I'm going to do is I'm going to label these edges with types, okay? So now an S means a tie is a strong tie, a W means it's a weak tie. 5 minutes. Okay. And I've labeled these here with weak ties because we might expect, okay, these bridges to be weak ties. Now here's the Granovetter idea, okay? The Granovetter says, suppose that we have a triad, right, where two of the links are strong. He says that strong links are likely to be closed, triadically closed. That if you're a really good friend of mine and he is a really good friend of yours, right, then it's likely that we're at least some kinds of friend. Maybe not really good friends, but it's likely that we know each other, okay? So, and we see that here, strong link here, strong link here, strong link here. What's another example? Where's one that has the property that I want? Strong link here, weak link here. Okay? Suppose we have as a hypothesis, okay, that if we have two edges of a triad, okay, that are strongly connected, okay, then there has to be, right, the third link has to exist as well. Everybody understand? If I've got strong here, then there's got to be some kind of edge going this way. All right? If that is true, then the only kinds of connections between these two cliques can be weak. If we have a local bridge has to be a weak tie. Why? If this is strong, okay, and there's any other strong link coming out of here, okay, then say this one here, if A to B is strong and D to B is strong, then A to D would have to exist, and therefore this would not be a local bridge. All right? So the claim is, right, that local bridges, right, should be weak ties. Now, why is that important? It's important because we would expect, for example, these people up here are all closely connected to each other, right? Strong paths between everybody, okay? A couple of, maybe a weak link here, but everybody basically, I can move from anybody to anybody else in a strong way. These people all pretty much see and know the same thing. These people pretty much all know the same thing, right? If B here is looking for a job, he's not going to know very much that D doesn't know. Or rather, D isn't going to know very much that B isn't going to know. D is not going to be very helpful for finding a job. If D knows about a job, likely B knows about this job. Where is D going to learn? B going to learn something? It's going to learn something from down here. So local bridges are very important, right, for this flow of information. All right. Now, to conclude, let me tell you how this can actually be affected in wage rates. All right. I'm going to very quickly describe a model by Jim Montgomery. Jim Montgomery is a very interesting guy because he has a PhD in economics. His first job was at Northwestern University, I believe in the economics department, and he is now a sociologist at the University of Wisconsin, meaning that he took a big voluntary wage cut in order to write on sociology rather than economics, okay? Here's a model that he wrote and published in the American Economic Review in 1991, okay? And this is going to be a model of referrals and the effect of neighborhood structure on wage rates. We're going to imagine that workers live for 2 periods. Half of the workers are high-ability workers, and they produce 1 unit. And half of the workers are low-ability workers, and they produce 0 units. And workers are observationally indistinguishable from each other. So if you're a firm, and every firm wants to hire 1 worker, okay? If you're a firm, okay, and you look at a worker, you can't tell whether that worker is high or low. A low productivity worker is worth nothing. A high productivity worker is obviously worth something. What is the profit to a firm? It's the employee productivity minus the wage. So if the wage is positive and you get a low productivity worker, you're going to lose money. We're going to assume that firms are risk neutral and that there's free entry. If there's free entry, we would expect firms' profits to be 0, okay? Therefore, also because of free entry, wage offers should be equal to expected productivity. So if we ran this model, this thing only for 1 period, and half the workers are good and half the workers are bad, what should the wage rate be? You want to have your expected profits equal to 0. What is the expected ability of the worker that you hire? 50% of them have productivity 1, 50% of them have productivity 0. What's expected productivity? Louder? 0.5, thank you, 0.5. All right, so what should the wage rate be in order to have 0 expected profits? 0.5, right? Okay, that's simple. That doesn't get you into the AER. Okay, so now we're going to have, we're going to add a time structure. That workers at time 1, they only work for 1 period, and then they kind of go into retirement, but they know people of the next generation. Okay? They know time 2 workers. So each time 1 worker has a social tie to somebody with a probability, and we'll call this tau. And the larger tau is, the more cross-generational links there are. Okay? Now, conditional on having a tie, it's going to be to the same type worker with probability alpha greater than 1/2. All right? If alpha were equal to 1/2, you just know random people. If alpha is greater than 1/2, there is homophily in links, right? That I tend to know people who are like me. If I'm productive, I tend to know productive people. If I'm unproductive, I tend to know unproductive people. The greater alpha, the more you can predict about a person from knowing that he or she is linked to me if you know how productive I am, right? Okay. And the assignments are all random. So, all right, so that's the model. All right, that's pretty simple. Firms hire period 1 workers, and there's, through an anonymous market, I'm almost done, wage rate, the market clears at some market wage. Productivity then occurs, and every firm learns its workers' productivity, okay? And then it's now time for the second period. I guess I forgot to say, we can assign the social ties at any time. It doesn't matter when. But the firm can set a wage rate or choose not to hire a referred worker from his worker in the second period. So Time 1 workers, so I guess what happened, the way to say this is that at the beginning of time 2, firms can make referral offers to friends of their current worker, okay, if they want. Time 2 workers, and there's going to be some wage rate, WRI, for these referral offers. Time 2 workers decide either to accept an offer or to go into the anonymous market. The anonymous market then clears at a wage rate, which is the second period market clearing wage. Production occurs and we're done. And what we want to do is we want to study the effects of alpha and tau on this, that, same thing, and this, okay? So let's see what's going to happen, okay? To begin with, only firms with type 1 workers in equilibrium, and we can compute all this, it's really very simple. You should look at the paper. Only firms with type 1 workers, which is to say productive workers, will make referral offers. Referral wage offers are actually distributed on an interval. It's not worth talking about this. The reason why is that it's possible that a single type 2 worker could have 2 friends who are of type 1, and so therefore he's got market power. Okay? And if there's market power, then in fact you're going to need a distribution in order to get equilibrium. This is something that was a big thing back in the 1970s or 1980s, and Jim obviously knew about that. What's interesting is that the second period wage rate is going to be less than 1/2. Why is the second period wage rate going to be less than 1/2? Because because firms with productive first period offers, with productive first period workers are going to make referral offers, right? And those are going to be taken in equilibrium. So the anonymous market is going to end up with more unproductive workers than productive workers, and that's going to lower the wage rate. Profits in the second period are going to be positive on average because of the possibilities of hiring a referral worker, or at least, because of the possibilities of hiring a referral worker. And the interesting thing is that first period wages are going to be greater than 1/2. Why are first period wages going to be greater than 1/2? If there was only one period, they would be 1/2. But the value of a worker to me, a first period worker, is in fact the sum of 2 things. It is the profits that I get from the worker today plus the value of the referral that I'm going to get tomorrow, right? And in competition for that worker, that's going to force the wage rate up so that it's greater than 1/2, okay? So we can see how social structure is moving us away from the anonymous market. Now what happens if we increase either the informativeness of the referrals or the density of the network? Namely, the more likely it is that any given worker has someone that he can refer, okay? Well, what's going to happen is that market wage rate in the first period is going to go up because now there are more opportunities for informative referrals, more opportunities for referrals or more informative referrals, right? So that's going to increase the wage rate in the first period. Profits in the second period are going up because you're more likely to get a referral that's going to be useful, okay? And because there are going to be more referrals going on, the anonymous market is going to be filled with lower quality people as these things go up, right? Namely, people who know only bad people, who are therefore more likely themselves to be bad workers, and consequently wages in the anonymous market go down, okay? So what we see essentially is that social structure creates inequality, okay? It creates inequality here because it allows for sorting of some kind, all right? It takes this difference in skill and it makes it to some degree apparent to the firm, and in equilibrium, the firms trying to exploit this information end up spreading the wages. So that what happens in the second period is that good workers are more likely to get are likelier to get referral offers, and those are going to be at a higher wage, okay? Therefore, the anonymous market is going to fill up with low productivity, with workers without referral offers, and those are going to be 2 kinds of workers. They're going to be workers that are not productive, a lot of them, and then there's going to be some workers who are productive but happen not to have the right contacts, okay? And so we see this inequality kind of emerging, and noticing that the inequality has, kind of it's not perfect sorting, okay? And remember, you can just leave alpha fixed and increase tau, the density of contacts. And so just adding more social structure creates these effects, okay? So we've been talking about different kinds of social networks and different ways in, how different ways in which social structure might appear. And this is the first model that we've looked at where we can actually see economic impacts of this. Now there are surprisingly few models that I can think of in the literature that do a good job of saying, let's actually stick this into a labor market or stick this into a financial market and see what happens. This means that this is a ripe area for research, okay? You've had a chance to read everything here. This stuff is not hard to work out. I could spend 5 minutes explaining it, but I think actually, given the amount of time we have left, I am not going to do that now. Here's a paper that you might enjoy reading. Nan Lin is a sociologist at the University of North Carolina, a really profound thinker, I think, about social capital. There's a nice book on it. Felicia Tian is one of his students, and here is a paper talking about how people find jobs in China, exactly what Granovetter was talking about. And you can read, you probably have by now read the conclusion, okay? It goes to show that this is not just an American phenomena, it is an international phenomena. There are studies that have been done in Russia, studies that have been done in Europe that all show that distinguishing between strong and weak ties is an important thing. They work in different ways in labor markets. How they work in different labor markets depends a lot on the culture of the country. So the way that they work in China, as reported here, is different perhaps than it is in the United States. Well, maybe I'm not so sure about that, so I won't comment on that. I'll just leave that alone. You should follow up on this if you want. Now that I've just put up a really interesting looking slide, I'm going to stop here. And I'll be happy to talk to you over the next week about more about these kinds of things. If you are interested in pursuing research in this area, I would love to talk to you about it. My expertise, I should have said this at the outset, my expertise is in economic theory. Don't show me a data set, I might fall asleep. But that's actually not true. But I don't, when you have people like Chris Tabor and Xiao Fu here, you don't really want to talk to me about econometrics, okay? I am happy to talk to you about anything you want to talk about, but in particular about how one might construct models that make some of these things more apparent. The reading list contains a few other good models that I think are very important. There's a model by a guy named Tony Calvo-Armengol and Jackson, which the paper doesn't get very far, but it is interesting to read. There's a very important paper on the dynamic persistence of inequality by Glenn Lowry that I think you should read if you're interested in inequality. Someone is talking, yes, Bhaskar is talking about intergenerational inequality. The Lowry paper is an important theoretical model that talks about that I would have talked about if I had had time. It's a bit of a complex model, and you need to know dynamic programming to read it. Dynamic programming is one of those things that if you've been in your macro class, you know dynamic programming. Otherwise, actually what probably is true is you don't know anything about dynamic programming, but you know all about the MATLAB code that you need for dynamic programming. Yeah, some of you are saying, yes, that's true. It is worthwhile exploring all of these things, and as I said, I'm happy to talk to you about that over the coming weeks, or the coming week. Thank you.